Good morning. Thank you. Thank you. My name is Arun Gupta. I work for Amazon Web Services. And today with me, I have Tiffany.
Bonjour.
That's where my French stops. She can talk a lot more, but that's where my French stops. So we're very excited that there are a lot of sessions going on at DevOps France. This is the first session of the day. And we're excited that you chose our session. So we'll talk about what do you do or what does it take to deploy microservices on AWS Cloud. And we'll particularly look at the stack. We'll look at, it's a very deep dive session essentially. Stay tuned with us. You can look at different ways by which you can talk to us, email, our GitHub, our Twitter handle, different ways you can connect with us. So we're looking for all different ways for your feedback. Feel free to be talking about it. In terms of the agenda, the way this is laid out, it's a 3-hour deep dive tutorial. So think of it as a show and tell. And so we'll show some stuff and we'll talk about it and keep going around it. We'll give you a quick introduction on relevance of microservices and sort of how we are building the application. Then right away we'll jump into, we'll take a look at 3 different parts of stacks, so to say, on how to build this application. We'll take a look at it particularly around containers. We'll take a look at it, Amazon ACS and AWS Fargate. Fargate was a brand new introduction at reInvent 2017. We'll talk about how do you what does it take to deploy your microservices using Kubernetes. And then finally, we'll talk about the same application that is being built using the AWS Lambda. So essentially, the same application built exactly using all these 3 different platforms. And as part of that, we will show you what does it mean by local dev test? What does it mean by deployment? What does it mean by building deployment pipeline? What does it mean by monitoring? What are my options for Canary deployment? For each of these full set of microservices. This is a very code-driven session. All of the work that we have done over the last few weeks is available in a GitHub repo, and I'll be sharing that the introduction with you as well. The slides are as well very much in the GitHub repo as well. So let's jump into it. This is something I tweeted a few weeks ago. People generally think that monoliths, the moment you say monolith, they get afraid, oh, you're still doing monolith? You're really old. Or if you're doing microservices, that's the new cool thing. I think the key part that you want to think about is, what is the business problem that you're trying to solve? If your problem is to really be more agile, innovate more rapidly, be able to adapt multiple languages, be able to release more frequently, and if those needs are not meant by monolith and microservices is the answer, then yes, go that route. But otherwise, you don't have to go that route. Because microservices does bring a set of additional complexities. AWS Cloud provides a lot of tools for you to simplify and manage those complexities very easily. But microservices is not a free lunch, so you need to be aware of that part of it. So with that background, let's take a look at it. What are the key blocks that you need for building your microservices? And how does the AWS Cloud help you build that? Well, of course, you need compute capability. There are lots of ways by which you can do compute on AWS. EC2, very traditional, spin up a VM, run whatever stack you want to do, you can do that. In terms of containers, we have lots of offerings as well. We have ECS. We'll talk about that in detail today. AWS Fargate was introduced at reInvent 2017. You can do Elastic Beanstalk. And of course, Kubernetes, which was, again, a brand new service which was introduced at reInvent of last year. So lots of ways by which you can do that. There is, of course, Elastic Container Registry, where you can publish your images as well. Typically, when you look at, compute is typically one of the biggest pieces because that's where your business logic goes, but you also need to think about in terms of storage, where I'm going to store data. And in terms of when I'm storing the data, what solutions do I have? I'm looking at relational databases. I'm looking at NoSQL databases. Can I do Elasticsearch? Can I do just plain S3 storage? S3 was the very first service that AWS created. It is typically peaking at millions of requests per second in a day and has trillions of objects into it. So it is certainly one of the most volatile, most versatile storage capability that AWS has. You're also looking at how do you integrate these different applications, different microservices? Do I need a queuing Do I need a notification service? Do I need an email service? So you start looking at those different components, and AWS again has managed services for all of those. You need to look at, how am I gonna front end my service with a load balancer? Do I need a cloud front? Do I need a Route 53 hosted zone in which, which is where I'm gonna access my service? And we'll talk a little bit about Route 53. API gateway is a critical part of your, when you're building your microservices. Is that sort of my front end by which my users are gonna access the microservice? Can I throttle it? Can I rate limit it? Can I charge it? Lots of different ways. More components. When you're building microservices, again, another key component that you're looking at is the developer tools. Do I have the support for deployment pipelines? How am I building my application? What are tools available to me for collaborative editing? So Cloud9 is a tool that is extremely popular within our customers on how we can do collaborative editing very easily. And last but not the least, what you're looking at is some monitoring and logging solutions that, how can I do when I'm building a microservices and my request is going from one microservice to another and so on, and until the response comes back, how do I trace that end-to-end invocation of the microservice? What capabilities do I have for logging, filtering on them? So again, the key part is these are sort of the main components that we look at microservices. And if you look at the service names over there, AWS has managed services in each of those. And to me, one of the biggest parts of managed services is the undifferentiated heavy lifting that you don't have to do. You can continue to focus on your business logic, your application logic, innovating on behalf of your customers, and if you need a notification service, just spin up that service, access it, and be done with it. So that's sort of the whole idea of using a managed service. So let's see, what is the application that we're going to be looking at today for our use case? It's a very simple application that we're building. The application, the big box outside is sort of my application. And application has 3 microservices. There is a web app microservice, a greeting microservice, and a name microservice. Web app is shown in the blue color because that's the only microservice that is exposed public, because that's where my client is talking. And you can see sort of the small blue box on the top on my application. That's sort of a security group that I've configured for my application, that this is how my client really talks to the web app microservice. Then the web app microservice talks to the greeting microservice, say, give me a greeting, how I greet my user. And then it talks to the name microservice, give me a name on who am I greeting back. And then it returns a response back. So these 3 microservices are really talking to each other. Now, each microservice could potentially be running as a container, and we'll talk about microservices and containers in a second. But once you're building this in a containerized environment, potentially stateless microservices, then you have lots of instances of these microservices running. Now, when web app is trying to talk to greeting microservice, how does it know which instance to talk to? So that's where you have this concept of a box around each of the microservice, around all the containers, which is a service discovery. So, I need to know a service name by which I can conveniently call that service. And I don't care which instance is serving because they're all stateless microservices. So that's sort of the way you go. And then web app is shown in blue because it's the only publicly exposed microservice, and greeting and name are internally exposed. I don't need to expose them. So throughout the deep dive, when we are talking about it, we'll be talking about exactly how this application is built, what is being done to publicly expose them, to scale the microservice, to the service discovery. Those are sort of the key components that you're looking at when you're building a microservice-based architecture. So let's jump straight into building your application. And what is it that we are doing to build our microservices-based application? In this case, what I end up choosing is Wildfly Swarm. Wildfly Swarm is a Java EE compliant application server. It's a Red Hat open source application server. And then Wildfly Swarm is, the biggest advantage is, first of all, leverage the Java EE expertise, but it adds other components to it, which makes it very microservice friendly. The other big part of it is also gives me a standalone jar file. I can say, here is my application logic, bring in the different components. It's very modular architecture. So using that modular architecture, it brings in the components that are required, and then it allows me to very easily create a fat jar, so to say. And with that fat jar, for example, if I'm just using JAX-RS, and then I have my application logic, now that fat jar is very easily transportable because I'm using standard Java terminology, and that fat jar could be done as a container, run on a Heroku, run on any cloud platform that you care about, and this will just work very well. Now, I'm using Wildfire Swarm here, but by no means I'm restricted to that. The GitHub repo actually has a pull request by which you can actually do, and thanks to Emily and her team, there is a pull request pending on the GitHub repo by which you can easily build this application or package this application using Liberty Profile. So that's the cool part about it, because the application is using all standards. There is nothing proprietary about it. So that's kind of fun. So what we're going to do is, throughout the deep dive, and this is a deep dive, so you really want to ask, show me the code. Less talking, show me the code. So throughout the slide deck, when you see show me the code, that means we're going to switch gears, and we're going to ask you, we're going to show you some code here. So what I would recommend is, if any deep dive you go to, you always ask the presenter, show me the code. Less talking, more code. So let me switch gears here. Thank you, Tiffany. So what I have here is my IntelliJ. And well, first of all, let's go to a GitHub page here, okay? This is my main GitHub page where my microservices greeting application is deployed, okay? All the code is available here on the GitHub repo, and I have this same GitHub repo open in my IntelliJ here. If you look at it here, it's a Java Maven-based application, of course. So I have my pom.xml. Here is my source, and I can look at my Java application. It's a simple greeting endpoint. In here, I have, it's a very standard JAX-RS endpoint. I'm saying this is the path where it's exposed. I got some logger. If you call this endpoint using HTTP GET, return a text response, and it's just simple hello. So nothing fancy business logic, but it returns a hello message for you. We also have some code fragments here for X-ray, and which we'll talk about a little bit later, so I won't dig into the details. But think about your application logic as just simple return hello. Then, of course, I have my application, which is sort of the bootstrap class for JAX-RS that is required. And then I have a startup bean. Again, I'm doing some stuff around X-ray over there, but we'll get back to it when we get back to it later, okay? Let's look at the pom.xml. Here's my pom.xml. In pom.xml, I have a whole bunch of properties over here that has been defined. Then I'm using Wildfly Swarm bomb. Then I'm using a whole bunch of other dependencies that are coming over here. The key part to look at it is, because I'm using AWS Java SDK for certain parts of it, I don't have to package the entire AWS Java SDK. I'm looking at the parts that really matter to me. So later when in the presentation, when we look at Lambda particularly, I'm not saying bring the entire SDK. I'm just saying bring the Lambda Java core. So that allows me to keep the jar file size really small. And that is very important because when you are deploying microservices, particularly as containers or as Lambda functions, it takes time to have download a bigger image. And it kind of is an extra cost that you have to incur. So really look at sort of the minimalist approach, how you can keep the jar file small, which will keep your container image small and the runtime efficient. Keep going over here. I got some dependencies, of course, defined. That's how I compile it. Here's a Wildfly Swarm plugin that really allows me to fire up the service and test it very easily locally on my machine here itself, okay? And then I have a Docker profile. Using Docker profile, the advantage is this is a standard Maven language. I have a Docker profile. I can just do Maven package, and I give it the Docker profile, and now my Docker image is generated. So very easy. And for the Docker plugin, I'm using the Docker Maven plugin. And that particularly is pretty cool because there are a couple of Docker plugins that are prominent, one by Spotify, the other one by Fabricate team at Red Hat. This is a particular one that I like because I've been working with the team for a very long time, and they're actively supporting it as well. All I need to do is just need to tie my phase and goals together, that package and build. And similarly, if I do Maven install, it's going to push the image to my Docker Hub repo as well. So that's pretty cool. Just the way I have a Docker profile, I have a Lambda profile as well, because Lambda, when you are running up a serverless function, then you need a deployment zip. And I need to have certain specific dependencies over there to be included to make a fat jar over there. So I'm using the Lambda Java core. This Lambda Java core is not required in the Docker profile, for example. So the way you package the jar file is a bit different for Docker and for Lambda. So we keep going down here, and I have my Maven dependency plugin, which is using sort of the assembly.xml and how my zip bundle needs to be packaged up. Okay, so let's take a look at it on what my application really looks like. So I am here in Microservices greeting directory. I'm going to say maven wildfly -swarm : run. So all this is going to do is going to package my application, and it's going to run the application locally on my machine itself. Because that's sort of my first step. I just want to test what that application looks like. So let me open up another tab here, and I'm going to go to Microservices name, okay? And I'm going to give the same command here, wildfly swarm run. And I'm going to open up another tab here, and this time I'm going to go to Microservices web app, and I'm going to give the same command here as well, okay? So what I've done is 3 different repos, and I've given Maven wildfly swarm. Each service is fired up. They're running on different ports over here. So if I go back here, my wildfly swarm is up and running over here. Again, wildfly swarm is up and running. This is for the name service. And finally, when I come back here, the service is fired up. And and here, again, it says the service is up and running. So just in a second, it'll show up the message. This error is a known error for the wildfly swarm team. So really, huge props to the wildfly swarm team to help me get along and be able to rapidly be more agile to fix the bugs as we were moving along. So now all my services are up and running. So what I'm going to do is I'm going to just say curl http localhost : 8080. When I do this, it just returns a response called as hello Sheldon. Okay, I mean it's a simple REST endpoint. So then I can say I want a different name to be calling me back. It says hello Penny. Then I can say hello 3, and it returns a different name. Just a very simple service by design, but it shows the logic, and what the service feedback really looks like. Right, let's switch back. All right, I think that says you now.
Okay, cool. So now going into the whole microservices and containers, and how containers basically help with having microservices. So what are some reasons that we like using containers for microservices? So the first one is that it's a single entry point with a single command. Next is that microservices, they encourage a polyglot culture, and containers enable that as well. There's no impedance mismatch. You can have all of your dependencies for your application are all packaged together, so you don't need to have that all separate. And then your containers, they don't affect the other containers. It's all pretty isolated, and that's how we like our microservices to end up being. And then also, if you think about it comparing to like VMs, it's a lot faster to spin up your containers. It's a lot faster to scale up and scale down than it is with a VM. So basically, if you're just running a container, it's pretty easy. You could just spin it up locally using Docker for Mac, Docker for Windows, or just like Docker on Linux. So let's go into showing it with Docker deployment. So I'm going to go and switch over again.
I'm going to shut down. I'm going to shut down the previous running to avoid the port conflicts here. And if I go to this directory, here you go.
Okay, cool. So all this stuff is on the website. So if later on you want to go to AWS samples and microservice deploy options, it basically walks through everything there. So like there was the whole like creating the images and everything. So it would be starting over here. So basically, if you're running it on your own machine, you can just use a Docker Swarm. So you can just go and do a Docker Swarm init. So I'll just go to my terminal. Oh, it's already part of it. Kidding. So basically, if I go and enter the apps.docker. Oh, where are you?
We are in that directory already.
Okay. Cool. So I can just use Docker Compose, and you can deploy with that. In the Docker Compose file, it has all of the 3 microservices in there. So like if I just showed it, you can see that there's the different services and the setup for all of those. So can just use Docker Stack Deploy with the Compose file to set up the application.
So we just build the application using Maven, and we could have prepared the image using Maven package-p docker. That gives me the Docker image, and now I'm using Docker Compose to test it all on my local laptop.
Yep. So now, like, if you've used Docker before, you can just go and curl on localhost. So since if we wanted to look at the web app service, like you can go to port 8080, which is defined over here in the ports. So if I just did the curl for 8080, you can see what I was showing earlier with, so it's just like, there's the greeting and then there's the name. And if you wanted to look specifically at the different like endpoints, you could go to those as well. So say if I went to just greeting, I would be able to see just the greeting part itself, for instance. And then I am going to go and remove it so that doesn't cause any conflicts later. Okay, cool.
So this is one of the most common ways we are seeing people testing it on their local machine very easily, because now you have a Docker Compose file. All the images are baked into your local registry. You put it into a Docker Compose, and then you fire up, and then you're still able to make sure that the services are able to talk to each other. With Docker Compose, you can, of course, scale up your services, scale down your services, so still understand how a lot of it would work if this were to go into real production. So definitely worth taking a look.
Yeah, and then the image are just being pulled from Docker Hub for what was built earlier.
Maybe we'll take a pause and see if there are any questions so far. If not, we'll keep rolling.
And the reason for the constant switching back and forth is because it takes longer to switch between things on a single laptop than it does otherwise. So, yeah. Okay, cool. So basically, if you're running a bunch of containers on like your local machine or in the cloud, for instance, you may be running like hundreds, thousands of containers. And you can do that in minutes instead of having to, say, have a giant application, monolith application. So now you can just have all the different microservices, the different parts, and spin them up quickly. But then there's the question of, well, how do I go and scale that? Doing it manually can be pretty tedious if you have hundreds or thousands of containers. So say you have a bunch of availability zones, and you're trying to scale across all of those. So you would want something to do your scheduling and orchestration. You could create something to do that specifically. You would want something to handle all of the clusters that you have, whether you want to scale up and down those clusters, whether you want to add security groups for those. You have things like placement engines, whether you want to, say, bin pack your containers. So having to do all of that stuff manually can take a lot of time. So the whole goal is for having like orchestration tools to be able to do that type of thing for you. So for us, we have a bunch of options for that. So for management, so handling all of those types of things, we have Amazon Elastic Container Service or Amazon ECS. There is also Amazon Elastic Container Service for Kubernetes, which is currently in preview. If you haven't signed up, you should go to, you can just search up EKS in AWS on Google or Bing or something and sign up. And then for those, there's multiple hosting options. So you can have everything running on EC2 instances, or there's this concept of technology called AWS Fargate that we launched at reInvent, so in around like November or so. And basically, for that, you don't have to worry about the underlying instances. And right now, that's available with ECS and will later be available for EKS. And then to finish the whole thing, there is Amazon Elastic Container Registry, or ECR, for you to store your images on AWS. So basically, at each layer, you can just pick. The goal is so that you can pick what you want to do. It's not just one specific thing. It's whatever makes it easiest for you to run containers on AWS. So right now, I'm just going to go into just ECS and AWS Fargate. So like the previous image before, it just replaces the specific like scheduling, orchestration, manager, placement engine stuff with ECS itself. So ECS would handle all of that. So there's a bunch of different tooling and things that make it so for ECS that you can do your production workloads. So we have things such as you have the option for different networking modes. So there's like AWS VPC, there's bridge mode. There's the option to do things like CloudWatch metrics. You can get things such as CloudWatch logging, and then you can create alarms, et cetera, based on what those metrics are. And it has really deep integration with other AWS services, so such as CloudWatch, whether you want to use a bunch of the other existing services that were shown like earlier on, you can easily do that without having to create your own plugin. It's already included. So like ECS itself makes it so you don't have to worry so much about managing like your clusters, but you still have to do, if you look at your instances, for instance, in those you have all your tasks that are running, and within those you have, for every single instance, you have your ECS agent, you have your Docker daemon, you have your ECS AMI, and it can be pretty tedious when you have a bunch of instances and having to go and manually upgrade those yourself. So like say if you're now looking, instead of just at one, I have to go and upgrade it in every single one of those. Say something is out of date, maybe I can create a script, but it's still a lot of work. So basically, we came up with, customers were telling us, okay, I don't want to deal with all that stuff. I just want to deal directly with creating a task. So task is just a grouping of up to 10 containers, but I just want to deal with my containers. I just want to make my application. I don't want to worry about all of that stuff. Do it for me. So with that, we created AWS Fargate. So you don't have to worry about what version am I on. We handle all of that stuff for you and upgrading it and everything for you. So let's go a little bit into some of the ECS constructs. Who here has used ECS before? Okay, cool. So if you have, this is going to be familiar to you. So we have the concept of a task definition. So I just mentioned tasks. So tasks are a grouping of up to 10 containers, and they're running all together. But you write that with a task definition, and in your task definition, you put things like the image names, where they're from, CPU memory. We have the concept of cluster. So the cluster is basically an isolation boundary. In ECS EC2 mode, it would be around your different instances. In Fargate, it is around whatever you decide your task, whatever task you want in it. You can do different things to run your task. You can do run task or create service. So if run task, if you run it and it fails, you have to start up again. Create service will make sure that whatever desired count you have is always running. So I'm going to now switch back over here and kind of jump into some of this stuff. Did you intentionally go? Okay. Yeah, so hopefully people can read that. Okay, so basically you have a family, so that is the name of your task. And then within it, so this is an example for Fargate. This basically just does a check to see if everything matches Fargate. You put your networking mode. In Fargate, it has to be AWS VPC. I'll go into that more later, CPU memory, and then you can put all the different container definitions you want. So just the name, and then where the image is, and then the container port. So it's the same idea for like name as well. It's set up the same way. Web app has some additional things where you can set environment variables. So for the different, to be able to talk to like the greeting and name if everything is on a load balancer. So then you can just add all of that stuff in there.
And one other thing to be seen here is the recommended approach for ECS is to typically use a ALB, an application load balancer, because that way you can create very easily do path-based routing, and that's sort of the recommended approach as opposed to ELB, which is typically for one service. So because then that is an additional cost to you.
Yeah, and so you can do things like if your path is like /resources/greeting, or maybe it's resources/names or whatnot, then you can have it do it based on that path. Especially if you end up having the ports being the same. This one is not. But so if you have that, you can go over, there's multiple ways to be able to run everything on ECS. You could use the console. You could use several of the different CLIs that are out there that we have or others have made. And then there's also like CloudFormation. But I will first start with using the console. Like if you've never used ECS before, it is the easiest way to go because you can see what everything is and what's happening for it. So if you just go to services, you can just go straight to Elastic Container Service.
1 second.
Oops.
How many of you are familiar with AWS console? Oh, good majority.
Sweet.
Okay, so we won't dig into the tutorial for console then.
Yeah, so basically there's just all the different services that you can get on AWS, they have over here, and you just pick on the different ones. So like if you were dealing with instances, you go to EC2, or VPCs, you go to VPC. So for creating a cluster, you basically just go to the clusters, and you can create a cluster. So you have multiple options. So currently it's just in US East 1 where we have Fargate available, but it'll continue to be other places. So you have the option of using Fargate. There's also the EC2 modes, both using if you want to do it with Linux or if you have applications that are with Windows, you can also do it with Windows, which we released sometime in the last like 6 months or so.
So the important part to understand is Fargate is the only one which is in US East 1. ECS, which is the EC2 mode, is available in a much wider set of regions. Now, so if you have data sovereignty requirements where you want it to be in your region, then maybe you can look at the EC2 mode. But if you're okay that I'm more interested in Fargate, then just go with US East 1. And then, of course, we are always looking for feedback from our customers on how and which regions do they care about. So if there are regions where you would like Fargate to be available, make sure, we shared our email ID in the beginning. Make sure let us know, because then we'll talk to the product management team and give you a requirement accordingly.
Yeah, so like if you've never used ECS before, it's easiest to just start with doing Fargate. You basically just go, next step, give it some cluster name, so I could just call it DevOps, and then click Create. And, well, if you just go and view it, there's your cluster. And one of the things about the cluster, as I mentioned earlier, you can have it with your instances or with Fargate, so you can just see both EC2 and Fargate. And then with the task definitions, you can just go, and so there's a bunch of existing ones that have been created, or you can just create a new task definition. And then there you also have the option, do I want Fargate or EC2? And some of your tasks could be compatible with both, depending on how you write it. So you can just put in the name. There's different roles you can have for integrating with different services, task execution role for if you do anything with ECR or CloudWatch, and then you can just put your task memory CPU, and you have the option of either like adding a container and putting everything in manually here if you want, or you could copy and paste the task definition into configure via JSON, so you don't have to do anything with it. So yeah, you would basically just like go and you could just run it from your task definition or run it from the cluster. And then there's also the ECR, which is listed in there as well. So if I just go back there, you can also go to your repositories. Okay, so for the people who have used ECS before, or if you're looking into like just starting looking at it, you basically use the same type of task definition schema as you do with what you would have known as ECS before with like EC2 mode. There's just different parameters that you go and add specifically, such as if you were using bridge mode before, you have to now use AWS VPC, but you can use that also in EC2 mode. So basically, like with your instances in EC2 mode, your instance would get an elastic network interface. It would get its own IP address, and it would have a security group for the entire instance. In AWS VPC, every task gets all of those things. So you can just have like the IP address just for your task. You can have security groups just for your task. So depending on how fine-grained you want that to be. So you use the same APIs. So like as I was showing in the console, you can have the option of picking whether you want to do Fargate or EC2 mode. It's all in the same place. If you use the CLIs, you do the same things. There's just other flags or a few things that you have to change depending on which one you're running. And then because of everything being able to be on the same cluster and the few changes, you can easily run both like Fargate and EC2 in the same cluster or move between one or the other. Okay, so I'm going to go back and show you some ways to go and run with Fargate. So one of the really easy ways of going about it is using the Fargate CLI, which was created by John Piñata. So basically, you just download it, and you can easily go and you can just create a load balancer. So you can just have it, so you'll end up going to port 80, and it'll create everything for you for that load balancer. For the greeting, all you have to specify is like, all right, so what load balancer am I using? What's my memory? What image? What port? And what path? And it will, by just doing those, you would already have your greeting service running for you. And then you can do the same thing with the name service. If you go to get the URL of the load balancer, then you can go and add that information to the environment variables. So for the greeting service and the name service, so they know how to talk to each other. So if I go and, so this, we already ran this beforehand. And so basically, if you just do info for that, it would give the load balancer. So there's this here. And then, so if I just do the curl on that,
HTTP.
Well,
Oh, there you go. Yeah,
yeah.
perfect. Yeah. So a little bit more background. Now, this API, the Fargate CLI API, was created by John Piñata, who's a solution architect at AWS, and this is basically a GitHub project at this point of time. But it is available to you for you to take a look at it, and we are looking for early feedback from you on how this API should evolve. So definitely file issues, send PRs on what this should look like. And then we are looking at it in the long run, how this could possibly be integrated as part of the AWS CLI itself, so that you have the tools available to you right as part of the AWS CLI as opposed to downloading some other tool. And the other cool part that I like about this is when you are to create, if you look at the Amazon architecture or AWS in general, building services over there, you have to pull in different services to build your application. This particular CLI provides that abstraction where, I'm an application developer. I've created a Docker image. Just take this Docker image and run it. Behind the scenes, it creates your task definitions, your application load balancers, your target groups. All the magic is happening behind the scenes for you. From your perspective, what matters is I'm just using a simple CLI and doing the thing for me.
Yeah, so and then if I were to just like do the same thing but /0, you can see like earlier that it just changes the name as it's going through the array for that. And then there's there's a bunch of different other ways to do it. So you can do things using the ECS CLI. If you are using Docker Compose and you like using that, you can use the Docker Compose file with the ECS CLI. There's other things such as using CloudFormation. You could have it just do everything that you need for your cluster, and then you could have the option of, say, using the AWS CLI and running all of your services, or you could package everything up into CloudFormation. So if you were to just click deploy to AWS, it would just start everything up for you, and it would just start running after a bit.
So the cool thing about this is, with one CloudFormation scripts, just literally one CloudFormation script, I have everything packaged up. I mean, I have sub-templates, of course, as part of it, all uploaded into an S3 bucket. But then with that CloudFormation script, you can tell your customers, hey, you want to mimic the environment, click on this link, and they will deploy that CloudFormation in their environment, which will create the ALBs, the target groups, the services, the Docker images, the ECR, all the components that are required. It will create those components in their environment, and then they can mimic it.
Yeah, sorry.
Yeah, go ahead.
So yeah, you can just go and create like your VPC, your different subnets, private, all of your routing for it, your different security groups, your ALB, and then you can have multiple files together so that you can separate it. So like for this, you can have like the master, which has the greeting infrastructure, etc., together. And then so if you just go into like name, you can see here is how you would write it, that same task definition, but using CloudFormation, and then creating target groups for it. And basically, if you just run master, it will do everything you need for you and start up the application. Any questions on that? Okay, so I guess I'm going to be basically switching back and forth. But so you have the option of setting up CloudWatch logs. So then you can go through and see all of the logging information for it, as well as you can see the different, like the metrics using the graphs that they have there. So if I were to hop back real quick, so like if I were to, which one is it running?
Yeah.
In the Fargate?
Yeah. Now, because when we looked at the Fargate CLI, there was no cluster name specified over there. So it assumes a default cluster name or default region, because right now Fargate is only supported in US East 1. So that's the cluster that we are looking at it. I mean, of course, you can create your own cluster and specify that as part of the CLI.
Yeah, so like everything was run as a service, so that way if it fails, it'll start again, and also so you can use it with a load balancer. And then if you look inside that, you can see things like what's the target group, what port is it listening on, what VPC, what subnets, what security group, and you can also see the specific task or tasks that are running for that. You can also then go and see metrics like how much CPU is this task using, or how much memory is being used for my service. And then you can also go and look specifically at the logs. So you can see if this was scaled easily, but like you can see all the things that are happening in there as it goes and sets itself up. So you can see at the end, it's like executing your Java for your web app swarm.
And all it's doing is just pulling in the CloudWatch logs and showing them integrated into the console. You can still go to your CloudWatch service and take a look at the logs right there itself.
Yeah, so if you want to see like individual ones, you can poke through here, or if you go to CloudWatch, the service itself, you can, if you just went over there, you could go and see everything that you've run before and all of the different logs that you have there. Which was, I guess, that. So I'm going to show one quick thing. So like if you go to back to the services, so if I were to click on the task definition, so within this task definition, so in web app, it is there is a configuration. So you can have if you're running in the console, you can just click a checkbox to turn on CloudFormation for logging, and it'll have everything set up for you. You can change it if you want to. But if you go over to CloudFormation, you can just go to this specific log group and in this region, and it'll go there for you. So that just makes it a lot easier. So you have a bunch of different things with pricing. So like pricing is based on your CPU and memory, how much you're using for that. There's like at least 50 different options that are out there. You can find that on the Fargate website and how much it costs for that. Billing is based on, it's charged per second. And then you can also have things that are the task level resources. So instead of like with your instance, you have your CPU memory for what your instance is. In Fargate, you would have it for your task. So you just specify the CPU and memory for your task itself. And so running it with like using that ECS orchestration in general is not any extra charge, but like for Fargate, it's just like, what are you using? So I guess I'll turn it over to you.
Yeah, I can do that. Thank you. Thank you, Tiffany. So think of Fargate as serverless containers, where you are not worried about the infrastructure, where you're not worried about which EC2 instance, where you're not worried about, I need to scale my cluster. You just give us the container, and we run it. You scale it, and we just take care of it behind the scenes for you. So that's what we want you to think about in terms of Fargate. That's the technology that's what it enables it. So the common question customers ask us, all right, cool. I'm coming to Amazon. You got container offerings. Which one should I choose? So let's take a look at it. How do we see this? So here I have Amazon ECS cluster, the big box essentially, and then I got 3 services, not my services, not my web app name and greeting, but essentially my 3 services that I want to deploy over there. And this ECS cluster is spanning 3 different availability zones. That's sort of the recommended architecture for high availability and resiliency. That's important. So I have 3 different subnets in each of the availability zones. Now, what I could do is I could create the cluster such that I have EC2 instances. So now when I'm deploying EC2 mode tasks over there, they're running on the EC2 instances. And in the same cluster, I can have Fargate mode task launched as well. So ECS cluster in that sense only becomes an administrative boundary. So you can really easily look at it that how can I take the same ECS cluster, deploy EC2 mode tasks or Fargate mode tasks, and we have customers who are migrating from EC2 mode to Fargate mode. So at Tel Aviv Summit, which was about a few weeks ago, there was an excellent talk given by Shimon Tolz, who's a CTO for a company in Tel Aviv. And he talks about exactly why they migrated, how they migrated, and some of the tooling around it. So I would highly encourage you to take a look at it if you're looking into those options. But the point being, ECS cluster is sort of your entry point. Once you have an ECS cluster, then the way you're looking at microservices, certain times you want a microservice to be attached to a particular node because it has certain requirements. And then because you want them to sit together. And in certain times you don't care. Just run it and scale it for me. That's all it matters to me. So this is how we want you to think about it. Switch gears now. How do we do deployment pipelines with ECS? Now, if you take a look at this, this is sort of the architecture for Amazon.com, which was about 4 years ago, 2014. This is a very popular article on all things distributed. And if you look at Amazon.com, it is really built as a set of microservices. Each of those microservices are really talking to each other with the well-known interfaces. They're all acting as a black box. That's how this whole architecture is. Now, in 2014, we were doing about 50 million deployments a year to keep Amazon.com up running. So we have, of course, a lot of tooling around it to keep that running. And a lot of our customers are very much at the scale of Amazon. And even if you're not at the scale of Amazon, then you still need deployment pipeline. So we took our experience that was inside Amazon, and we released it as a code pipeline, as a managed service. So if you're looking at a managed service where I don't want to set up a cluster myself on what my master, what my slave is, how I'm going to distribute the bills. But if you're looking for a fully managed service where the pipeline is being done, AWS Code Pipeline is our managed service. So let's take a look at it, how we can easily create a deployment pipeline with AWS Fargate. Okay. What we're going to do for that is we're going to use the tools, again, our AWS managed services for that, and let's take a look at it. So as a developer, I'm just pushing code to GitHub repo. As soon as I do git push, things should happen for me. And what are those things? Things are, it should run the tests. It should make sure it should build the repo. It should figure out if there are any compilation errors. It should go through the performance regression testing. It should have those multiple stages. So those are the typical capabilities that I'm looking for in a deployment pipeline. So what I'm doing is I am setting up a simple AWS code pipeline, just simple managed service. Go to the console, say I'm going to create a code pipeline. Code pipeline comes with a bunch of predefined stages, like a source, build, deploy, such and such. So those are different stages that are available to you. What I'm doing is I'm just configuring it that as soon as there is a push made to a GitHub repo, let me know. It's just a simple GitHub hook. That's what I'm configuring it for. And then I'm saying I'm just requesting the AWS code commit service in that case, because that's where my build is running. So I'm saying, OK, push has happened in the code pipeline. I'm visually creating it. Now go ahead and build my application. And then as part of the build, once the build is done, then I'm going to push the Docker image up to my ECR, or Elastic Container Registry. So git push, build, and push to ECR. There is a deploy stage in the pipeline. That deploy stage then says, OK, take that ECR and deploy it to my ECS cluster. And of course, the ECS cluster kind of pulls the image from my Elastic Container Registry. So that makes it really easy. So once again, git push, the code pipeline is configured for a GitHub hook, which then delegates it to code commit to build my Docker image, which then pushes to the Elastic Container Registry, and also tells the ECS cluster that, OK, the deployment needs to be done, and ECS cluster then pulls it. Now, of course, when you have different images, each image is sort of an immutable version because it has a name and a tag. So the important part is to make sure that the commit ID or the commit hashtag is attached to as a tag itself. So all those things are automatically taken care of it for you yourself. At any point of time, the cycle breaks. Of course, your application in production continues to stay as is. Okay. So let's take a look at it on how this can be done. Now, this was done again. This workshop, this tutorial really stands on the shoulder of giants. So this was again, this particular reference architecture was built by another solution architect at AWS. His name is Jeremy Cohen. So he has exactly created on how this thing needs to be done. Okay. So again, I'm referring back to the GitHub repo that we've been talking all along. So all I'm going to do is I'm going to click here, and I'm going to. Typically, you'll see in AWS land, when we like to automate things, CloudFormation is the most natural thing because it has very tight integration with all of the AWS services. So we write up a CloudFormation template. We tell you exactly where you launch it. It creates all the resources, and it's very reproducible again and again and again and again. So all I'm doing here is I'm creating a stack. I'm saying Fargate continuous deployment. Launch type is Fargate, of course. I need to specify my 3 microservices essentially, because that's where the change needs to happen. So if any repo changes, now in this case I'm creating one pipeline, but I could very easily split this CloudFormation to say create 3 separate pipelines because that's sort of my real world. So throughout the tutorial, we're showing different design patterns because there are lots of ways by which you can skin this cat. So take a look at it, what makes sense to you. But this is one of the design patterns. So in this case, I'm just using the 3 repos. I'm going to specify Arun-Gupta here. And I also need to have a token. So I'm going to just go here, go to this link. I'm going to generate a new token. So this is a Fargate pipeline. Okay, I can generate a new token. I can say Fargate pipeline 2. I don't need any specific access. generate a token, copy this value, go back here, and paste it here, okay? And that's all. That's all I need with that CloudFormation template. And of course, I need to acknowledge that, okay, it's going to generate and create resources for me on my behalf. And once I click on create, it's going to go ahead, run behind the scene. It takes a few minutes for this template to run because essentially it's creating my code pipeline, my code commit, my triggers, my VPC networks, everything that is required. And it just makes sure that is done and the IAM roles. But what I've done is I've already created this for us behind the scenes. So I will just look at the stacks that already exist, okay? So this is the stack that I created earlier today. And you can see this was done like about a couple of hours ago. So if I look at the Fargate pipeline here now, okay. Not showing the outputs.
You have to click it.
Oh, here. Oh, the resolution is all messed up. So that's why it's doing it differently. Okay. So first of all, the pipeline is already created. So here is giving me, as part of the pipeline. So let's look at the pipeline first anyway. So here is my pipeline. And it says source, build, and deploy stages. Those are very simple stages that it's explaining over there. Okay. And this can be done in a very visual manner on what these hooks need to look like. And then if I go back to my CloudFormation template here, it is also giving me a service URL. So very convenient. I open up this URL. Oh, the service is not working. Of course. We won't try to debug this live here. It's a CloudFormation template. But the point being, this is exactly what it should have done behind the scenes, created all the services. So what we can do is we can take a look at the pipeline here itself, and we can look at the details here. So it says succeeded 1 hour ago. So look at the details. It says, OK, this is a cluster that has been created for you. In the cluster, this is the Fargate pipeline cluster, which it created behind the scenes. So see, for some reason, it's saying, the name and the greeting service are up and running, but the web app service is not running. So you can at least start digging into the details for what reason the web app service was not running. So if I look at here, for example, then I can look at the tasks here. Then it still says it's pending. So if I look at it for the details, so then I can keep digging into it, what's going on and why the service is not up and running for me. But the point being, all of this infrastructure is automatically created for you and is just ready to be used as is.
Yeah, and then like on the services page, you can click events and see what has happened with your service. You can also go and look at your stopped containers and see, or your stop tasks and see why did my last task stop. And
all right, one of the last things that we're going to cover as part of ECS is how do we do Canary deployment for ECS? So now, this is again a reference architecture that has been created. So a lot of the design patterns that you would like to call them as are created as reference architectures. And each reference architecture in that sense comes with a ready-to-use CloudFormation script. Okay? So in this case, the way the Canary deployment is done, the main feature that you're looking at it is Route 53 has this routed waiting policy. And so what you do is you have your application up and running in one particular cluster. You bring up a new application. So you have your green application running. You bring up your blue cluster. And then using Route 53, you can set up a weighted algorithm saying, OK, to begin with, 100% of the traffic goes to one particular ALB. And then over a period of time, transition from the green ALB to blue ALB until blue ALB becomes real. And then you can set up your alarms that at any point of time, if the request is not going through, like if the traffic from the blue service is not meeting the standards, then you want to fall back onto the green as well. So you're really introducing a canary. Now, unfortunately, the term canary, the way it was introduced was pretty cruel. The coal miners would really go into the coal mine. They'll take a canary, and if something happens, and if there's a toxic fume in the coal, the canary would die first, and the coal miners could run out. But in this case, we are hoping that when we introduce a blue build, which is a canary, and if things fall, the blue build dies, and only a small subset of users are impacted. So that's sort of the part that is over here. Of course, another part that you want to think about here is, what is it that is really triggering the deployment? ECS also has this concept of an event stream, which is first around nodes and second around containers. So at any point of time, there is a step function, which is again a managed service at AWS. It's looking at that event stream, and once the blue cluster is up, it's looking at that event stream. Okay, the blue cluster is up, then it changes the routed weighting algorithm for Route 53 and slowly starts shifting the traffic over there. And the AWS step function is also monitoring that how much traffic should be shifted. So literally, if you click on this reference architecture, it deploys it shows you exactly how you can do a blue-green deployment with ECS. So at this point, we're gonna stop for ECS and see if there are any questions around ECS or Fargate before we switch gears to Kubernetes. Okay, I think we'll keep going then. So we will take a break. It's about 1 hour into the deep dive, so maybe we'll take a break in about 20 minutes. Sound reasonable? Yeah? Okay, cool. Let's do 20 minutes then. All right. How many of you are using Kubernetes in production today? 4 or 5 hands. How many of you are dabbling with Kubernetes? I mean, playing with Kubernetes or using Kubernetes in dev today? Okay, okay. That's very typical that we are seeing in terms of in production versus playing. But how many of you are aware of Kubernetes? Hopefully, a lot more hands. Okay, very cool. So this is not a Kubernetes 101 in that sense. It's purely talking about really how do you create your microservices using Kubernetes. So if you look at the recent CNCF survey, which is Cloud Native Computing Foundation, which is where the Kubernetes project is hosted, and AWS is a platinum member for it, and I'm the board representative for AWS in CNCF. So I'm very actively involved in the Kubernetes community. If you look at the most recent CNCF survey, it says 57% of Kubernetes today runs on AWS. And that is purely organic. That is really not much of effort from AWS or offering a managed service or nurturing the community in that sense. But that's a pretty good number. And customers have done some really fantastic things around Kubernetes on AWS. But if you look at how do you set up a cluster of Kubernetes, you need to set up a master. Ideally 3 masters across different availability zones so that the master is available. In the master, again, there are components like API server, controller, scheduler, DNS. And we have seen deployment topologies where some customers have actually even split up those different components of master. There are recommended ranges that if your cluster has a certain number of pods, your master should be on a certain EC2 instance type. And if the number of pods increase, the master instance type should increase to accommodate that increase. And those bands are narrow. So somebody has to constantly monitor and update your master accordingly. That's the master part of it, which is typically the stateless part of the control plane. Then the second part of the control plane is also etcd. Etcd is the persistent state of the cluster. So anytime you create a service, that state goes into the etcd cluster, and then the master reads it from there and then does the action upon it. Now, should my etcd be sitting with the master on the same instance, or should the etcd be sitting separate? Who's going to back up my etcd? Should it be encrypted? Who's going to snapshot it? So there are lots of questions when it comes to your mind, and there are lots of ways by which you can set up a Kubernetes cluster. And then, of course, at the bottom, what you have are the worker nodes. And then you attach those worker nodes. That's where your containers are really running. So that's a very typical architecture for setting up a Kubernetes cluster. But then there are 1,000 ways to run a Kubernetes cluster as well. If you go to kubernetes-aws.io, you will see about 20 ways by which you can set up Kubernetes today on AWS. So customers have been asking us that setting up Kubernetes isn't a trivial work. It's not for the faint of the heart. Managing and operating a Kubernetes cluster, it requires some hard work here. So there are tools available for that. Yes, that simplifies it, but it is still a lot of work. So customers are asking us, run Kubernetes for me. If I take you back to 2014 for a second, ECS was launched because customers were asking, hey, we want to run multiple Docker containers at a scale across availability zones. There was no Kubernetes at that point of time. That's the reason ECS was created. AWS roadmap is 90 to 95% governed by customers. So customers were asking, run Kubernetes for me. So we announced EKS, or Elastic Container Service for Kubernetes. This was announced at reInvent of last year. And the service is today in limited preview. And what that means is you can go to aws.amazon.com/EKS, sign up for the service, and when your name shows up in our list, then we give you access to limited preview. Or otherwise, definitely work with your account managers, technical account managers, your solution architects on expediting that. Okay, you know what? I want the access faster. That always works sometimes as well. So let's take a look at it. What is it that we are doing with EKS on simplifying that pain? So to recap, our standard Kubernetes distribution today looks like master, etcd, and worker nodes. They're all spread across multiple availability zones. Okay. So what we are doing is we are providing you with, as part of EKS, we're giving you a managed control plane. And what that means is, when you come to AWS, you can say, OK, I want to create a Kubernetes cluster. We give you a managed control plane. With that, you get 3 masters and 3 etcd nodes. Okay? And in our case, we have taken an opinionated approach where the etcd is not on the same node as master. So essentially, 6 EC2 instances are actually provisioned for you, 3 for the master and 3 for the etcd nodes. And we take care of first of all, etcd is encrypted, and we take care of managing that etcd for you behind the scenes. And of course, we have managing the master. We choose the right optimum size for the EC2 instance for the master. We take care of upgrading the master for you if the number of pods are increasing. So we take care of all of that for you. So from your point of view, you just go to AWS console. You say create an EKS service, and then it creates a cluster for you, and that's it. Now, very much like ECS, you still have to bring in your worker nodes and say, here is my worker nodes, and attach it to the EKS control plane. That's about it. So because that's where your nodes are running. So the control plane is running in an AWS managed account, and the worker nodes are running in the customer managed account. That's sort of the model, very much like ECS in that sense. So what happens is, I have my EKS control plane, and I have my worker nodes. I attach my worker nodes over there, and then one of the core tenets of EKS is 100% upstream compatibility. And what that means is the kubectl that you are using from the upstream, that's the same kubectl that you can use to actually deploy to a Kubernetes cluster. There is no internal versions of Kubernetes being maintained. There is no behind the firewall, any patches being made. Anything that we are working on, first of all, is done 100% in open source, and then contributing back to upstream. There are several components, well, at least a couple that we are looking at. One is the CNI plugin. If you look at the Kubernetes architecture, the way networking works in Kubernetes is using CNI, which is Container Networking Interface. What that enables you is how you can do networking using a variety of networking plugins. There's a Flannel, there is a Weave, there is a Calico, all sorts of different networking plugins. So you can plug in the networking plugin of your own choice. For EKS, what we have created is a new CNI plugin that is again done out in the open source, which is giving you native VPC networking. And I'll talk about that a little bit later, but that's sort of the whole premise. We are also looking at how in kubectl, if you're operating in the AWS world, the way you do authentication and authorization is based upon IAM. In kubectl today, there is no IAM integration. So we have made integration in client Go, which is sort of the library that the kubectl uses behind the scene. And then we are also working with Heptio, which is one of our partners, on how to add IAM authentication capabilities to kubectl itself. And those work are all done out in the upstream, essentially. So the point being, you will be able to use the AWS CNI plugin out in the open source. You'll be able to use the kubectl, which is again out in the upstream, and be able to use IAM to authenticate to an EKS cluster. So that's kind of the whole premise of EKSs. All right, let me show what does it take to create an EKS cluster. Now, at this point of time, EKS is only available in US West 2, okay? And this is a preview console, so it's only a very, it looks like very developer-designed console, but when it's gonna be ready, when it's gonna be GA, or generally available, then it's gonna be integrated as part of the main console itself. But today, if you give us your account, and your account is whitelisted, and then you will start, you will get the instructions on how to set up a EKS cluster, how to bring the worker nodes, et cetera, in there as part of it. But then you will have access to the console as well. And what I'm showing with the console can also be done using the AWS CLI. But what I can do is I can create a cluster. And in the cluster, of course, I need to give it a cluster name. Today, the cluster is 192 compatible. Whenever EKS goes GA, whatever the upstream version is at that point of time, is the version that we're going to GA with. Now, one of the common questions that our customers ask is, what versions are you going to support? So when EKS goes GA, whatever the upstream version is, that's the one we're going to support. And we're going to start with that. If you look at the Kubernetes versioning scheme, it is major.minor.patch. So 1.9.2, that means 1 is a major, 9 is a minor, and 2 is a patch. We will not give you a choice between the patch versions, because patch versions are typically CVEs, bug fixes, security patches. So we'll automatically upgrade that for you. Between the major and the minor version, we'll give you a choice to either automatically upgrade it or manually upgrade it. So that's sort of the way we are looking at it. And so you will have that option. Either way, whether it's automatic or manual, the cluster will be a rolling upgrade, so that there is no downtime for your application, either for accessing the containers or for management of the cluster itself. That's an important part. So this version will be whatever the version is at that point of time when EKS goes GA. I need to give it a IAM role here. I need to specify my cluster subnets and security groups, and that's about it. I'm setting up 3 different availability zones, and then give the subnets and put them in here. Okay. Now I do have a cluster already created. So if I look at my EKS cluster here, it basically says here's a master endpoint, Kubernetes version, status, and cluster on, and that's about it. So it's very easy to get started with it. And again, at the point that I said earlier, is following the AWS best practices, high availability, automatic resizing, automatic upgrades, and all those good things that comes along with it. Okay. Thank you. Any questions on it so far? Yeah. We'll talk about that today.
Yes, I have a question. How many times it takes to bootstrap an EKS cluster?
So typically what we have seen is if you are firing up a new EKS cluster, it takes about 7 to 10 minutes, because essentially behind the scenes, we're provisioning 6 master nodes, installing all those kubelets and all those things for you. So that's the time about it takes. All it's doing is behind the scenes is provisioning those EC2 instances and having it ready for you.
Okay, so it's provisioned using, I think, CloudFormation, maybe?
No.
So
No.
we don't have access to how it was provisioned? No.
You don't need to know exactly. That's the whole point. Because if I go back here for a second, if I change here, if I look here, I can say AWS EKS, and I can say, show me the help that is available. So this command is now available to me as part of it because my account has been whitelisted. And then you can start looking at it, okay, what commands are available to me? So I can say AWS EKS list clusters, and it'll list my clusters. So from your perspective, even if you were to kind of create a cluster here, you can just say AWS EKS, create cluster, and you specify those 4 parameters, and it'll provide the value. Oh, I think my AWS CLI is configured to a different region. But if I were to configure it to say US West 2, now I'll do the list clusters, and it shows the list clusters over here. Now, the other part that would be relevant for you is how you attach the worker nodes is done using CloudFormation. And what we do is we provide you a pre-built army that is based upon Amazon Linux 2. And we say, OK, here's a pre-built army because that army has Docker, kubelet, whatever components you need, the specific Kubernetes version that we have tested. So you can bring that army and connect it as part of to the master. That is using Amazon Linux 2, but the way we have built that army is using Packer scripts. And those Packer scripts are going to be open source as well. So let's say for some reason for your corporate you need a particular operating system, then you can use those Packer scripts and build your own army and bring them and attach to the cluster as well. Yeah.
Is it only EBS as a storage class, or is there any integration, tighter integration with EFS, or just external, like external NFS server?
So that is a very Kubernetes question as opposed to EKS question. So whatever is supported in Kubernetes, that's one of the core tenets of EKS. We are providing 100% upstream compatibility. There are no additional features that we are bringing as part of it. So if there is any support required for ZFS or EFS or EBS or any of that, then those are going to be all done in the upstream from our side.
I have one question.
Yeah.
Regarding the master cluster, can I put them in one VPC with different availability zones and attach my worker on it? Or it could manage different workers, mines and other workers?
So when you're creating a cluster, you can create it in a VPC as well. But what you will need to do is once you're creating in a VPC, then you need to have some way to make sure that you can download the Docker images from outside, or the Docker images need to be packed in there. So you'll have to kind of configure the security groups accordingly, or have like an internet gateway connected to the VPC so that you can do that. And all of your workers can sit in the same VPC as well. And I'm not going into the networking part of EKS particularly, but the way EKS works today is, if you look at the EC2 instance type, and each EC2 instance type can have certain number of ENIs or elastic network interfaces attached to it. And the number of secondary IP addresses that can be assigned by each ENI are predefined as well. So the idea is now on your EKS cluster, which is running in a VPC, you are spinning up a pod. So it says, because we are using the AWS CNI plugin that is providing you a native VPC networking, it says, oh, ENI, give me a secondary IP address. That secondary IP address is then attached to the veth of the pod, and we let the Linux kernel take care of the rest of the magic. So all the pods are given a secondary IP address, and all the pods can really then talk, because that's a requirement for Kubernetes. So now all the pods are given a secondary IP address from the associated ENI, and they can all talk to each other without going outside on the internet. And I would recommend to take a look at the AWS CNI plugin for Kubernetes. We also have a CNI plugin for ECS, and both of those are done out in the open source. So first is to take a look at those design documents, what they offer you. And second is Anirudh Atal, he's an engineer in the containers team at AWS. He's giving a talk at KubeCon 3 weeks, I think, in 3 weeks. And that is exactly talking about how we build those CNI plugins. All right, so I think let's talk about it, then we'll take a break. So when you're deploying an application to a Kubernetes cluster, there are certain basic application level concepts. Well, of course, there are ops concepts like a master, a worker, and a node and all those things. But these are the typical main developer concepts that you care about when you're deploying microservices. The basic concept is a pod, which is co-located group of containers that share an IP, network, volume, all of that. So the containers within the pods can then talk to each other using localhost. That's very easy, very simple. Then there's a deployment. You typically don't deploy a pod directly. You typically take the deployment, says, okay, what deployment is the declarative state of the pod. What that means is I want to run 3 instances of the pod. And if the pod goes down, then the deployment will bring it back up again. And so as part of the master, you have controller manager and scheduler, which will make sure that the pods are scheduled and continue to stay up and running. Each pod can be assigned certain metadata called as labels. And then those labels can be pulled together. It's a very loosely coupled relationship in that sense. So those labels can be pulled together to create a service. Because pods are ephemeral. Each pod is given an IP address, but if the pod goes down, it comes up on a different host possibly. It could have a different IP address. So you can't really refer to the pod directly. But the labels on the pod are always the same. So those labels are really used to create a service. And so service really is is a logical set of pod that is accessible by a name. So in terms of creating microservices, that is sort of your logical abstraction. That, okay, how does it going to look like? Okay? So those are sort of my key application concepts. So let's take a look at the Kubernetes application manifest on what do we have, and how does my Kubernetes application manifest look like for my application that we just talked about for ECS and now for Kubernetes. Thank you, Tiffany, for keeping this up. So here is my manifest file here. In the manifest itself, I can put all the services and the deployments that I care about. So I'm saying API version v1. This is a service. That's the metadata that I'm attaching to it, to the service. Now, I can specify the specification of the service, in which I'm saying the selector is app:greeting. That means the pod or the deployment that I'm creating should have that particular metadata. And that's how that pod is being pulled as part of this service. And I'm giving the name, protocol, and port. Same thing with name as well, but the selector here is app:name. And for the web app as well, selector, of course, is app:web app. And now I'm creating my deployment. In the deployment, if I look at the specification, if I don't give replicas, by default, the value is 1. And I'm giving the template of the pod. And here is my spec. And in this pod, I only have 1 container. This is my image name. This is my container probe. And in the container itself, I can start defining health checks. Now, back in the ECS land, if you look at it, when I specified the particular path, my health checks are automatically created for me by the Fargate CLI. So that's pretty cool. That's pretty awesome, actually. And here, if I specify sort of these liveness probes or readiness probes, then it'll automatically ping it. And it'll say that it may take up to 50 seconds for the first probe to be active, but once the probe is active, ping it every 5 seconds. And what happens is, if a particular pod is not meeting those requirements, that pod will be killed and started on a different host. So at any given point of time, your service is the one that you're talking to, and behind the scenes are only healthy pods. If the pod is unhealthy, it'll be terminated and restarted. We'll look at this X-ray daemon address a little bit later. I have something very similar for the name here. My path, of course, is different. For path and port are different. And then I have something similar for web app. And here, I'm using the environment variables. The way my service talks to each other, or the web app talks to name and greeting, is using environment variables. And in this case, I'm just giving a name and a greeting, host, port, and path. And if you look at the name host, I'm giving the value as name. Well, my service name is name. So that's all I'm caring about. So that's the value, because now my pods can automatically scale back and forth behind the scene. I'm just referring to the service by name directly itself. And that DNS, that's done by the kubedns add-on as part of Kubernetes itself. So that's sort of my simple manifest over here. All right, so what we're going to do is, I think we're going to take a break here. Maybe what time is it? Is it 10:54 a.m. here? So let's take maybe a quick 6 minutes break. We got a lot more content to go. We'll talk about application packaging. We'll talk about deployment pipeline. I'll show you a reference architecture using code pipeline. We'll talk a little bit about Jenkins X, which is a new effort by CloudBees. We'll talk about Canary Deployment using Istio. And then we will repeat, rinse, and do the whole thing for AWS Lambda. So a lot more exciting stuff to go. Please come back. Thank you. Thank you. Thank you very much for coming back. Hopefully more people will show up, start filtering back in. So as we were talking before the break, we looked at sort of a Kubernetes application manifest, which is one big file where all my services and deployments are all chucked in together. Now, how do I collaborate on such manifest files? And that's sort of the tricky part of it. How do I start repurposing some of the code? There's a lot of boilerplate code in that. And that's where your Helm charts kind of come in handy. So let's take a look at it. What are Helm charts? How can I use Helm charts for deploying my microservices to Kubernetes? Okay. So Helm is basically a package manager for Kubernetes. So think of it like Yum or apt or brew for your other operating systems. Think of this as a package manager for Kubernetes applications. It's basically a templating and a packaging tool. It defines a directory structure on where each of the deployment descriptor needs to go. And once you have that, then it creates called as a Helm chart, which is sort of the main artifact or a zip distribution, which can be uploaded in a Helm repository and then downloaded from a Helm repository accordingly. Okay. Talked about that part already. Now, there is a chart part of it. So you manage the chart part of it as on the client side. But then once the chart is deployed in a Kubernetes server, then you can manage the releases, different releases of the Helm chart itself. So let's try to understand how the overall architecture looks like. So first of all, of course, I have my Kubernetes cluster running on AWS. So Helm has two parts. There is a client part, which is running on your desktop. And then there is a tiller, which is running inside the server over here. Okay, so that's where the tiller part of it. So once you have the Helm CLI, you just say Helm init, and if your kubectl is configured, it's going to configure Helm for you automatically. Now, Helm runs on your laptop, as I said earlier. So you can continue to kind of create your chart files over there, which is a directory structure with all the templates and everything in there. So that is very useful for all of your CI/CD, for example, and then whatever you want to integrate with. Once you publish it to a Helm repository, which you can set it up locally, or there's a default Helm repository, then it becomes a chart. So you're locally playing with the template files, or you can publish it to a repository, you have a chart. The way you deploy an application to a Kubernetes cluster is you say, Helm, take a chart, and or I want to deploy an application. So think of as a WordPress as a Kubernetes application. As part of WordPress, of course, you need MySQL, and you need the WordPress core engine itself, and maybe some other images that are as configured as part of it. So all of those could be defined as different deployment descriptors, packaged into a chart file, and you can say, go ahead, deploy my application into the Helm repository. So by default, what it'll do is the Helm client will talk to the Helm repository, download the chart locally, uses gRPC to talk to my tiller server, which then talks to the Kubernetes API server and stores it in a local config map and manages your releases over there. So that's sort of your broader Helm architecture in terms of how these different components really work with each other. There is the only way the charts are stored into the Kubernetes API server or the Kubernetes control plane is using the config maps. Okay, so let's take a look at our Helm map and Helm chart and see how does it look like. So here I am. Here is my Helm directory. So if I look at it, this is my app. At the very top, of course, I have a chart.yaml. In there, I'm just providing some metadata. I can start specifying some versions. Then I have a values.yaml. Again, these file names are pretty standard, so you just use values.yaml. That's where I start defining what my values are going to be. So I'm saying it's just a key value pair, very typical YAML syntax. So greeting, name, web app, and Docker, I'm giving a tag. Because now, once I've defined these values in here, it's using mustache templating language. So I can start using these values throughout my different templates now. So if I look at in the templates directory here, this is where my templates are sitting. So if I were to look at, say, greeting service, is saying release.name, which is basically coming from the chart.yaml dash greeting. So that's sort of my service name is going to be. Similarly, I'm attaching labels to it, and I'm attaching selectors to it. If I look at the deployment, in the deployment is where is my very similar to my previous deployment in a manifest itself, but it's just using a templating language over here. So it makes it follow the dry principle where you're not repeating yourself. If you just change the number of replicas in your values.yaml, you can just refer to them right here in this particular configuration file itself. Okay. So if I were to go into the GitHub repo here, all I will do is I'll just say brew install Kubernetes Helm, and then downloads the Helm CLI on my local machine. I can do Helm init. Of course, you need to make sure your kubectl is configured for the right cluster. So you could look at it, kubectl config get clusters or get context. So if I go here, I can say kubectl config get context. It shows me I got a bunch of clusters running up over there. So it can show you all the clusters that are running. So you just need to make sure that you can say kubectl config set context and give it the cluster name. So you set up that context, and then when you say Helm init, it will install the tiller as a CRD or a resource descriptor in your Kubernetes server itself. And in order to deploy my application, all I need to do is I can just say Helm install, and I need to give it a name as well. So I'm going to say my app and the my app directory, and that's it. That's all it takes to really deploy this application into a Kubernetes cluster. So if you look back up here, I have a different context set up over here. So I can easily switch this to a different cluster. So let's say cluster.k8s.local. So what I can do is kubectl config set context, and I will just select this context name. Okay. Now if I say kubectl get nodes, it shows me the nodes in that particular cluster. Okay. This was done about 19 hours ago. So now I can say Helm init. If I do Helm init, well, tiller is already installed in the cluster, so that's good. Then I can say Helm install name my app, and I give it a my app. So with that one command, if I fire it up, it'll either install the application that is apparently it already exists. So what I can do is Helm delete purge my app. So I can delete the app in this case. So this will delete the app, which will basically go ahead and start deleting your deployments and your services and your pods and everything else. But once the deletion is done, then I can say, oh, now I want to install the app again. So if I say kubectl get service, it says the services are not running. Similarly, if I say kubectl get pods, it says they are in the terminating stage. So but once they're terminated, so the point being one command to deploy your entire application. And the other big part of Helm is how it allows you to collaborate now. Because now your deployment descriptors are spread across multiple files, and you can say, here is my pod, you work on the pod, you work on the deployment and the different parts of the microservices. So it's really a collaborative tool in that sense. So if we check again, this is gone. So now I can say Helm install name my app, my app. That's it. That's all the command it takes to get your app up and running in there. And now if I say kubectl get service, see my services are already created over here. And I can say kubectl get pods, and I can add a watch switch to it. So these are running but not ready yet because as the pod is firing up. So hopefully in a few seconds, the pods will be all ready to go. And then I can start accessing my services essentially. Okay, yeah, well, let's switch. Thank you. All right, so let's take a look at it. How we're going to deploy, build a continuous deployment pipeline with Kubernetes. So, but actually before that, I'm sorry, I'm going to switch back actually, talk something else also here in the GitHub repo. Yeah. So Helm is one of the ways, is probably the most popular way by which your Kubernetes applications can be deployed. But there are other very popular, other popular formats that are coming up along. One of them is Cassonnet. The other one is kubepack. So what I would recommend is if you go to the table of contents in this GitHub repo here, it talks about standalone manifest, it talks about Helm, it talks about Cassonnet, it talks about kubepack. So all the different ways, and there are very fully working samples on how you can deploy that. Now, another part that I want to talk about in terms of creating the cluster. The most popular way typically that we have seen our customers creating a Kubernetes cluster on AWS before EKS has been kops. So that's the tool that we have seen most heavily used. So if you look at create cluster using kops, it kind of gives you a full instructions on how easy it is to create a Kubernetes cluster on AWS. So all the things that I talked about earlier in terms of master and etcd and nodes, kops really simplifies that to quite an extent. So if you're looking at a community way of creating a Kubernetes cluster on AWS, then kops is what we have seen our customers using it. Of course, we have a managed service that should be going GA. Yeah, all right. All right, let's talk about deployment pipeline using AWS Code Pipeline. So once again, we talked about the concept and the background for AWS Code Pipeline. This is also available as a reference architecture. So let me walk you through how this reference architecture works, and then hopefully I'll be able to show this live in action as well. Once again, we're using Code Pipeline. To me, the big part of it is a fully managed service. I don't have to worry about it. So as soon as you do a git push, in this case, I could use code commit as a service. Could very well be a GitHub as a service, so where my code is hosted. It doesn't matter. But in this case, I'm just using code commit because that's another managed service by AWS. Anytime you make a change to your code, you do a git push to code commit. This will trigger a deployment. Well, it'll trigger a build of the service. And it's using code commit as the backend managed service to build your application. The build is done, then it triggers the Docker image, or actually pushes the Docker image to the ECR, or the Elastic Container Registry. Now, when you're creating the CloudFormation template, at that point of time, you need to specify the credentials for the Kubernetes cluster, because end of the day, it is going to deploy to your Kubernetes cluster. Those clusters are stored in a Lambda function, and they are fully encrypted, using KMS. So the point being, as soon as the Docker image is pushed to the ECR, it invokes the Lambda function. The Lambda function then uses those encrypted variables, and then it triggers the deployment to the Kubernetes cluster. And of course, the Kubernetes cluster pulls the image from the ECR. So this is the URL where the reference architecture is available. So if you take a look at this, and again, this is linked from the GitHub repo. So go to this URL. It talks exactly about how this architecture has been built. And once again, there's a CloudFormation template. Click on it, and it deploys it into your environment, and you're ready to roll. So now this is one of the ways that we can do CloudFormation or the deployment pipeline. I will show that in action, but I also want to talk about another tool, though. So let's take a look. So let me make sure I'm into CloudFormation here. Here? Yeah, that's what I have to change that, yeah. Okay, so I created this template earlier today. Generally, I like to pre-create my CloudFormation templates because it takes a few minutes for these to get up and running. But I have the Kubernetes pipeline here. If I look at the outputs here, well, I think it's in the pipeline here. Yeah, this is in the pipeline here. So okay, it talks about sort of the git code commit repo here. I can look at the pipeline URL. It's a very, it failed, what happened? Oh, you know what, I don't have my credentials configured yet. But the reason it failed is because the master branch of the code commit repo does not exist yet. So what I need to do is, if I have this pipeline URL, it also gives me the git code commit repo here. I can check out the code commit repo as soon as I push a code to it. The master branch is created, and then the first run of the code commit fully succeeds. So then every git push to the code commit repo will trigger a deployment, and I can quickly see how the changes are coming along. So that's again was done by one of the solution architects. His name is Omar Lowry. So again, a lot of solution architects from AWS has contributed to this workshop. So really want to give a huge props to him. But the tool that I want to talk about that is coming along pretty decently is Jenkins. Well, a lot of customers use Jenkins for their deployment platform. It is very popular, actually. But a new project that they launched a few weeks ago is called as Jenkins X. Now, that's something that I've been watching very closely. And the whole purpose of Jenkins X is to provide first-class CI/CD integration on top of Kubernetes. On a Mac, you just install the Jenkins X CLI. So just brew it, brew tap it, install it. Now, the way Jenkins X works is it requires RBAC and it requires insecure registries and stuff like that in your Kubernetes cluster. So if you have created a COPS cluster, then you can manually edit the cluster to enable all of that. Or you can say, hey, JX, create cluster, and it'll take care of creating a Kubernetes cluster for you on AWS using those opinionated approaches. So this is sort of the easiest way I've found how you can easily create a cluster. And once you do that, then I just have a simple repo. You could pick any microservices repo, like the greeting on the web app or the name. You need to import the project in JX, in Jenkins CLI, basically, because then it takes a look at it. It creates your Jenkins file. It creates your Docker file if it doesn't exist. It creates all the components that are required for it. And finally, you can just say, you know what, open up the console and just start pushing the code. So I think the developer workflow with Jenkins X is pretty cool. It's pretty simple. I found this to be very effective for a greenfield project. So if I'm starting a brand new project, a brand new cluster, all of that. But for a brownfield case where I have an existing cluster, I have an existing app, which is most of the time is the case, it's a little bit touchy and sensitive. So the project is new, but it's evolving very rapidly. The team is very competent. So I'm very optimistic about the project, and I'll be keeping a close eye on it. Carlos, who just walked in, he's going to be showing a demo of Jenkins X in his talk tomorrow. So if you want to get more details about it, feel free to stop by that talk. Now, if you are creating a EKS cluster, well, one of the things that we are doing as part of EKS is, well, I mean, you can create a EKS cluster, you can delete a cluster, you can upgrade a cluster, and all those things. Those are standard AWS CLI commands. Those calls are all logged in CloudTrail for auditing purposes. So that's sort of the integration available to you. And then when you are doing anything is happening in your API server itself, that you're saying you create a pod, or there's a log output coming from the pod, all those calls are put into CloudWatch. So out of the box, we're going to give you integration with CloudWatch and CloudTrail. I think I'm not going to show this one. I'm going to skip this. It's very straightforward. It just shows the entries that the cluster was created. So you can go to CloudTrail and see all the entries over there. So I'm just going to keep moving here. So let's take a look at it, how we do Canary deployment using service mesh. Okay. So what is a service mesh? Well, service mesh is there are services that are already existing into Kubernetes. Why do we need a service mesh? Kubernetes is just one of the orchestration framework. What you want is a platform that allows you to connect, manage, and secure your microservices, which is not likely an application or a orchestration framework dependent. Okay? So it really provides you a platform that works out of the box. Big advantage of this is it works with any language or any framework, and it's completely independent of that, because the way it is deployed is really as a sidecar. So what you're doing is, let's say in case of Kubernetes, what you have is a pod, or in the pod you have one container, and you download in our case particularly, we'll talk about Istio. So you can inject your service proxy as a sidecar container as part of the pod itself. And then that sidecar container is the one that takes over for all the service-to-service communication. The big advantage of that is it really decouples your application itself from the operational aspects. Because now, things like routing, things like service discovery, things like telemetry, you don't have to build logic for that into your application. Your application can stay clean, and all of these typical concerns can be now done at the proxy level itself. So really no change required to your microservices, but then these service meshes can provide you a lot of data over there. Something else that they're very good at is providing you a fleet-wide policy enforcement that, okay, which pods are now available or which services are now accessible or not accessible. You can literally apply that at a very high level. There is really no magic around there. Now, the particular service mesh that we're going to use is Istio. Now, if you take a look at it, the way Istio works is, it uses route rules. Well, first of all, you're looking at a Kubernetes cluster. In the Kubernetes cluster, you need to install Istio, first of all. So, because it installs all the key components over there, and there are several components of Istio. The names are like pilot and mixer and auth component. Once all of those components are installed, and each of those components play a role, but basically they enable that, okay, now your Kubernetes cluster is ready, or is Istio enabled. So then such a Kubernetes cluster start understanding a new deployment descriptor, which is using the kind as route rule. And in that route rule, you can start putting some values. So in this case, what am I doing? Let's see. I'm defining a route rule, and I have a specification. In that, I'm saying the destination is name:greeting. So basically, that's the service where it's guided to. And then I'm defining a route. And in the route, I'm saying if the labels are greeting:hello, then the weight is 90. And if the labels are greeting:howdy, then the weight is 10. So if you look at how typical Canary deployment is done in Kubernetes today, you have this concept of a deployment. Okay, the deployment is you can say I want to have 5 replicas of a particular pod. Now, if you want to introduce a new service, typically you will add a new deployment, and then you will gradually scale the older service down and bring the newer service up. But so that's one way of doing Canary deployments in Kubernetes. But that doesn't really give you the fine granularity that, hey, you know what? I want only 5% of the traffic to go to this new service. If you were to direct only 5% of the traffic to new service, and then in order to make that 5%, so have one pod running over here, you really have to scale this service up to 20 times of this service. So you have to run those 20 pods. So that fine granularity is not available in out-of-the-box Canary strategies for deployment. And this is exactly what it does. So in this case, because the Envoy proxy, Istio uses Envoy as a proxy, which is injected as a sidecar container for you. Because the Envoy is taking over the service-to-service communication, you can start enforcing those rules that, okay, you know what? Only 90% of the traffic goes to a service with this particular label, and the 10% goes to it. So you can still happily introduce your 2 deployments, scale them up and down the way you want to, and actually have much more finer grain control over how your services are being invoked. So let's take a look at the code here. All right. Thank you, Tiffany, once again. So I did this about 4 or 5 days ago, and that's the latest version for Istio at this point of time. All you're going to do is you're going to get the latest Istio, install it, and again, these instructions are all in the GitHub repo. So all you do is you just make sure your kubectl is configured for the right cluster. You apply and say, okay, install the istio.yaml, where all the components are installed. All the components are installed in a Istio namespace, so it kind of stays clean. Now, remember, we talked about no changes to the microservices here, but we still need to inject that sidecar container. So the way we deploy the application, we don't take it, say, okay, take my application and deploy it as is. I'm just saying kubectl apply, and I'm giving it, of course, a whole bunch of files over here, but I'm just using istioctl kube inject subcommand, which basically now takes my existing manifest file. So this is sort of my manifest over here, and it takes that manifest and it starts injecting. Okay, so let's take a look at this manifest for a second. Oh, thank you. So here is my service. It has a name greeting, labels name greeting. That's good. Name service is not relevant. Web app service is not relevant. Now here is my greeting service. So what I've done is, as I showed in the very beginning, our service is returning hello as a greeting. I just posted another version of the image, which is returning howdy as a greeting. Hello and howdy. Those are sort of my two basically Docker images at this point of time. So what I'm doing is, in this case, I'm creating a deployment with the name greeting hello over here. And I just have the tag Arun Gupta /greeting:hello. Okay. The key part here is to look at the label. So there is app::greeting and greeting::hello. Those are the two labels on this service. And if I go down, I have app::greeting and greeting::howdy. So those are the two labels. So on the services, I have the common tag is app::greeting, but then there is a unique tag as well. So if we go back here to the route 5050, I'm just saying name::greeting. That means both the services will be picked up. That's sort of my target. I'm using labels for picking up the service. And then I'm saying, okay, what is the service that I should be using to really pick for 50% and the 50% target over here? Similarly, I can do that for route 9010. I'm saying name::greeting, greeting::hello, and greeting::howdy, and 9010 split. So I can just use those kind of route rules to describe how much traffic needs to be directed, and in this case, is truly making 90 and 10%. Now, one other part to realize here is, when I'm doing the labels over here, 50-50, it's not like a coin toss and it's going to go over there. But the point being, if you look at about 100 requests, over 100 requests, they'll be equally split 50% of the time between howdy and hello images. So that's sort of the way it works. And yeah, so once you deploy the application, you just start accessing the application, and then you will see how the requests are coming along. Now, one of the issues I was having particularly was I deployed the two images, but one of the upstream, essentially the hello and the howdy images are both upstream images, but one of the images was somehow failing the health checks. And that's the issue that I was debugging with somebody on Stack Overflow in the Istio team. So hopefully that'll get resolved, but it's already tracked as an issue over here. So once it gets resolved, I'll just update the repo here itself. Thank you, Tiffany.
Mm-hmm.
Some other advantages that where Istio is very powerful is how it can start injecting fault. It can start injecting delays in your service. In a typical microservice architecture, you can't avoid that. That is bound to happen. Delays will happen for whatever reason, particularly if you're running containers across the network, across the cloud. So this is going to happen. Your services will start timing out. Maybe there's too much garbage collection happening, and the services slow down. You can configure latency. You can configure spikes of a service. You can have other undesirable effects. So let me show you a couple of examples of how those route rules can be configured to induce these kind of effects as part of your application. So this particular one, if we look at it, we're talking about we're introducing a 5-second delay in about 10% of the requests. So all I'm doing is I'm just creating a route rule, and I'm saying the destination, and in the root I'm saying label greeting::hello. So only for the hello service, not the howdy, but I'm saying introduce a HTTP fault, %10, and fixed delay 5 seconds, and that's it. That's all it's going to do. So take a look at it, how your services behave in that sense. Here's another one, a little bit more complex in this case. So in this case, what I'm doing is I'm saying the destination is name::greeting, match the web app, and I have version v2. Okay, so I have different versions of web app that are being deployed, and all I'm saying is delay all requests from web app v2 to greeting howdy by 5 seconds, and also about 10% of the requests. So you can actually, if you have heard the concept of chaos engineering that is becoming more and more popular, particularly in the microservices landscape, so it truly allows you to enable chaos engineering in your application. And the whole concept of chaos engineering is why you need to make sure that your applications fail miserably during dev and testing so that they don't fail in production. And that's what you're doing. You're inducing those concepts during your test cycle itself. And that's where it is very useful. I also want to throw up props to Chaos IQ. Chaos IQ is a company. We met these guys a few days ago, and they're building a Chaos toolkit, which really truly works in the Kubernetes land itself. And you can start inducing chaos engineering in a native Kubernetes way as part of your microservices. So really, make sure your services are failing more miserably in the dev and the testing stages so that they hopefully continue to work in the production. All right, let's talk a little bit about metrics, or monitoring rather. So now, if you look at the Kubernetes landscape, the way, there are lots of different components, and not just Kubernetes, but generally in containers, lots of different metrics that you want to measure. Well, first of all, there is node. And I'm particularly doing this with the Kubernetes landscape lens. You want to measure the node health. Then you want to measure the pod health. There are different tools available for that, cAdvisor or kubestate metrics. And then you can start looking at application health. I can start, if I'm using a Java application, I can start using JMX to spit out those metrics. Then I need a little bit more cluster-wide aggregator. So give me the health of the cluster itself. There are Prometheus, Heapster that provide me those kind of metrics. I need a data model on how and where this data can be stored. So InfluxDB or Graphite are some of the prominent data models where this can be stored. The metrics are good, but I need some sort of alerting mechanism that, you've reached a threshold and do something for me. Or alert an SMS or whatever, Slack channel, whatever needs to be done. And last but not the least, you need some sort of a visualizer on top of all of these where I get up in the morning and I can look at my heat map where my services are broken and what things need to be fixed upon. So alerting is good, but that historical background of the visualization is really important. So these are some of the tools that we have seen that are prevalent in the Kubernetes community. Of course, all of these tools would work with any Kubernetes cluster running on AWS. But what I want to talk about today is, again, because we are talking about AWS specifically, I want to talk about the managed service, which is X-ray service. So X-ray helps you with tracing requests, record the traces in an X-ray service, and view the service map of your distributed application. In our case, when you look at the microservice itself, we have web app, we have name, we have greeting. It really allows you to give a complete holistic view of how the application looks like. So the traces are recorded, and you can start looking at the service map. And the most important part is once you view the service map, to identify the potential bottlenecks, where things are failing, what things are failing, and how I need to look at it. I think that's the key part that you want to look at it. So what I'm going to do is I'll talk about there is an X-ray SDK. So you need to start injecting that code as part of your application. So it's a little bit more into the application itself, but it's available for a variety of languages. So you can start using it with any of. There is a in our case, I'll walk back to the application code. I'll start talking about it, how we are injecting AWS X-ray as part of it. You can, of course, do this for HTTP and HTTPS services, other REST endpoints that you're invoking, so you can start injecting over there. So it really allows you to get started very quickly, okay? So what I'm going to do is I'm going to switch to showing some X-ray monitoring, how easy it is. Now, in terms of monitoring with AWS X-ray, well, first of all, X-ray daemon, which is basically what collects all the information coming from different microservices, is fully open sourced. So you can take a look at that. What you do is you have to build, in terms of Kubernetes, you build a daemon set. And what daemon set is basically making sure that one instance of the pod is running on each node of the cluster, okay? So what I've done is I've built a simple image already. It's an X-ray daemon set. I can deploy the daemon set. And once I've deployed the daemon set, I just install my app using standard Helm charts. And that's it. I just access the application. OK, so let's do that. So what I'm going to do is I'm going to say kubectl config get context. It shows the contexts are there. So I'm going to, well, the context is already, I thought we changed the context. OK, just make sure set context X-ray gates local. OK, so kubectl get pods. So if I do the kubectl get pods here, my pods are up and running over here. OK, so if I go back here to IntelliJ for a second, now here is my startup bean. OK, this is the code that we were looking at it earlier. We didn't talk about it a lot in the beginning, but all I'm doing here is, as my application is coming up, I have a startup bean identified. OK, now when the startup bean is available to me, and this is, by the way, configured in my application here. So in my application, I'm saying here is a singleton bean. So this application will be eagerly loaded. This class will be eagerly loaded for me. Okay. Now in the startup bean, all I'm saying is set up a X-ray global recorder. By default, your application always tries to talk to the X-ray service. And if the X-ray daemon is not running, it will fault back. But then it allows you a control. If I go back into my startup bean here, I'm just setting up a context missing strategy. That even if the X-ray context is missing, don't worry, just keep going on. Because in my local dev environment, I may not want to have an X-ray daemon running. I may want to do this only for testing and staging and production environments only. So I've just set up a simple context strategy over here, and I set up a global recorder, and I start recording the results. Okay. So what I'm going to do is I am going to copy this command here, and I'm going to invoke the service. It says, hello, Sheldon. And do this a few times here. OK. Then I'm going to go back here, and I'm going to go to my console, and I'm going to look for X-ray. The service map, it takes some time to create it. We are in the right region. But what we can do is we can take a look at the traces here. Oh, what? Yeah. Oh, you know what? I think the X-ray cluster is set up in the US East 1 zone, not in West 2, actually. So if I go back to, say, 5 minutes here. Yeah, OK. This is basically showing in the 5 minutes. So what I'm showing you is a service map for how I access the service in the last 5 minutes. And if you look at it here, I can actually zoom it in. It's showing the web app, the name, and the greeting service. This is the client that it was accessing. There are additional clients that are being shown because those are sort of my health checks that are automatically happening for the name and the greeting by the Kubernetes cluster itself. I can select web app here, and here it starts showing me how many APIs are being served with 100% request or throttling or error, whatever is happening. Then I can look at the traces here. And here is the trace that I can look at it. And in the trace itself, it's saying, oh, this is a web app, this is a greeting, this is a name, how long is taking each service to invoke each other. So it's truly giving me that distributed map of my service. And this is where I can start identifying what my red hotspots are, which are the services that need further tuning, and I can start drilling down further on this. And the whole code for this is, of course, shown over here. I just took a snapshot and added it this morning. Here is the service map. Here is how a trace looks like. Now, something else that you also want to take a look at it, Istio is one of the service meshes. Conduit, is also a popular service mesh that is coming up. Used to be based primarily on Linkerd, but Linkerd was kind of tougher to start with. But if you take a look at Conduit here, and somebody from the community added instructions on how you can easily do Conduit. Now, the Conduit example particularly is not catered towards these microservices. They use their own sample app because you need to drive traffic in order to see the telemetry data. But hopefully, we'll have this sample converted to start using our microservices. So the idea is that here is a microservice architecture. How do you adapt it, to a particular tooling? Okay. Oops. Sorry. All right, that's pretty much my last slide over here. Now, one of the things that we showed you when we started the talk, we talked about how you can do Fargate and ECS together. So that is already available in GA today, but when EKS goes GA, to begin with, it'll be there in the EC2 mode. And then we have also announced the intent to have EKS and Fargate mode. So think about it, that you can just bring your part spec and say, take a part spec and run it. I don't want to set up a cluster. You manage the cluster for me. It's all done by you. So then it really doesn't matter. Bring your task definition, bring your manifest, and we'll just run it for you. We'll just scale it for you automatically. So that's sort of the intent with EKS and Fargate integration that we're talking about. Any questions on Kubernetes before we switch gears to Lambda? For what?
For the tracing you just showed earlier, the X-ray. Do you integrate with Zipkin?
So the question is for X-ray, for the tracing, you integrate with Zipkin. Now, X-ray format, well, the X-ray daemon particularly is open source. So in that sense, it could be used to integrate with other tracing formats very easily. But the X-ray format is pretty rich, and it provides a lot of data. So we encourage our customers to take a look at it. Okay, and I guess we'll keep going. This is sort of the last part of the presentation. We still have about 45 minutes to go, but let's take a look at it. How do we deploy the exact set of microservices? Now, this time using Lambdas, okay? So let me actually begin with sort of the key concepts, first of all, okay, for serverless. There are really 4 tenets as AWS looks at it. And these are the 4 important tenets. Well, first of all, there are no servers to provision from your perspective. Somebody is running a service in the background. So there are always servers running. So somebody is managing it. But from your perspective, you say, you know what? Take my Lambda function, run it, and scale it, and whatever it needs to be done, that's what it happens. Who's provisioning it? Who's paying for it? No. Your cost computing model is exactly that. Okay, you know what? I'm only going to pay for the compute time that when the compute is happening. But there is no cost for the storage also. That's the important aspect to understand. You never pay for any idle. And then the important part is how it just automatically scales with the usage. So think about Fargate, that is serverless containers. Think about Lambda, that is more, that is how the whole serverless kind of thing started essentially. If you look at the broader spectrum of offerings at AWS, well, of course, you have EC2, if you look at it on the far left. As part of EC2, you can spin up your own VMs, set up your auto-scaling groups. You can set up Docker, Kafka, Cassandra, whatever service comes to your mind. But then you are responsible for making it highly available, auto-scale it. All that logic is upon you. The second and the middle basically comes as managed, where I'm looking at it, for example, like EMR or Redshift or RDS. When I'm provisioning an RDS instance, at that point of time, I can say, oh, make it highly available. You have to explicitly make a decision and then enable that. So you are explicitly making that. And on the far left, it sort of comes out of the serverless landscape. What was the first AWS service that was launched? S3, yeah. That was the first S3 service launched. For the longest time, our customers were asking that when something happens in S3, give us an ability to do something about it. That's one of the main reasons that how AWS Lambda was created. So if you think about it, you uploaded a document in S3. I want to trigger a compute function, maybe resize it, maybe zip it, maybe encrypt it, and then put it back into a different S3 bucket. So there are like 18 triggers for AWS Lambda. People often confuse Lambda and serverless as one and the same thing. AWS Lambda is only the compute part of serverless. What really matters is how you look at the broader serverless landscape, how you have different triggers. And by far, if you look at the AWS cloud, there are 18 different triggers, S3 or DynamoDB or SNS. There are lots of ways by which the Lambda function can be triggered. So it's the overall platform that what matters in terms of how these things work together. So what I'm going to do is I'm going to jump into some of the Lambda basics and then right away talk about how do we create our microservices using the Lambda functions. So there are 5 languages that are supported today. So there is Node, Java, Python, C#, and Go. Those are the 5 languages that are supported on Lambda today. So you can bring those languages. You can literally package your function as a deployment zip, and you can say deploy it, and then it just sits into the console for you or in AWS, and then you scale it. There are different programming models with it. There is synchronous, there is asynchronous, and there are streaming programming models. Lots of different use cases for that. In terms of the resource usage, we just give you one dial, which is basically the memory dial. And with the memory is accordingly your pricing is done. And the CPU and the network are allocated accordingly based upon the memory dial. Okay? And of course, it has fully integrated with the IAM, VPCs, and authorization and all of that. So let's take a look at it, how my Lambda function looks like. Okay? Now, in this case, all I have is a public string. Well, this is a Java function. So in this case, I'm saying public string handle request. So handle request is sort of the method name that is coming from the interface. I need to implement a specific interface, is the method name coming from that interface. Then I say book, which is sort of my inbound payload, because essentially when my Lambda function is invoked, some request is coming in. So that's my inbound payload. Then there is context, which provides me a little bit more context about the runtime of the Lambda function itself. And then within the function, of course, is my method, which is sort of my business logic, which is what needs to get executed here. Okay. So let's switch gears. Let's talk about how my Lambda functions are packaged here. Thank you. Now, in this case, I wanted to, if I would have, well, because I'm using microprofile application server or Wildfly Swarm, I already have a JAX-RS endpoint written for me. And I just wanted to repurpose that endpoint for the Lambda handler. So I just used it a request stream handler, because then I'm just delegating it to the underlying JAX-RS endpoint. But if I were to write this as a brand new microservice, then I will just implement the regular request handler, and then I put my business logic in there instead. So there are different ways by which you can deal with it, but this code is all available to you here. Okay? So in this case, all I'm taking is the input and output stream, and I just delegate it to the underlying JAX-RS endpoint for doing all the business logic for me. And if I go back to, say, pom.xml here, and we looked at sort of the Lambda profile earlier, here's my Lambda profile. Here are all my dependencies that are defined over here. If I go to assembly lambda.xml, I exactly specify what format it needs to be zipped up in and what files I need to package in. So you can start looking at it, what needs to be executed. The important part to understand is you want to create a shaded jar. And the shaded jar is because you want to make sure that all your dependencies are included in the jar itself. So that it's a fully self-contained jar. Because end of the day, that code gets uploaded to S3, unzipped into your environment, and then it gets executed over there. So you want to have a full control of it in that sense. Ready? How do I deploy my applications? in the Lambda world. So we introduced something called as a serverless application model. So meet SAM, as I think is a very, as Tiffany was saying, it's a very cute, nerdy logo. I like it particularly. So let's take a look at it. What is SAM? So SAM, or serverless application model, is a DSL built on top of CloudFormation. It's extended and optimized for serverless. And as part of that, what you get is really 3 new resources. One is the API. Then you get, which is basically mimicking API gateway. Then there is a function, which is basically for the serverless function. And then you get a table, which is basically a simple DynamoDB table. If you think about an application, you typically need an API, a business logic, and a database. So it really allows you to build those applications very easily. And because it is built on top of CloudFormation, in SAM, you can put any CloudFormation construct as well. So that makes it very powerful. Okay? The important part here is to understand it is a fully open specification. So you can take a look at it, how the specification is done. And at San Francisco Summit, which was in 2 weeks ago, we also open sourced the translator. Because essentially, if you look at the SAM template, there is a translator component that runs behind the scene, which takes the SAM template, creates a CloudFormation out of it, and then deploys the resources behind the scene for you. So the SAM translator component is now open source as well. So let's take a look at it, how my SAM template looks like. So let me walk you through this. It's a little hard to read here, so but we'll see. Let's look at the first point here. So, well, first of all, I'm saying this is a CloudFormation script, but a transform needs to be applied. That's where my SAM translator kicks in. Then I'm saying, oh, this is a AWS serverless function, and that's a new resource that we're introduced as part of SAM. Of course, I give my handler my runtime. I'm saying, here's my code URI. My code is living on my local repo. I'm doing Maven package, and it creates my zip bundle, and I'm pointing to the local repo. Then I'm saying, OK, I just want to enable X-ray as well as part of my Lambda function. So I just add another attribute, tracing:active. Remember, in case of Kubernetes and ECS, we had to deploy an X-ray daemon to the cluster. In this case, this is fully natively integrated. There is no need for you to deploy it. You just add this attribute, and the requests are then accordingly start to be traced. I'm referring to a table name that I have an environment variable called as table name, and then that is referring to this table, which is basically a DynamoDB table here. And last but not the least, I'm saying, OK, here is where my request is being serviced. Here is the API where the request is being serviced. Then, of course, the template will have far more details over there, which will talk about, oh, what is my Swagger definition for the API? So right in the SAM template, my Swagger definition is specified itself. And based upon that is how my API gateway endpoint is created. So one concept is SAM, okay, which is sort of the SAM template itself. But then you also need to download the SAM API or the CLI. And that CLI allows you to really operate on your SAM template. And that CLI really comes with 2 commands. One is the package, which basically says, OK, you are pointing to a zip bundle on your local drive. I'm going to take that zip bundle. I'm going to upload it to S3, because that's how Lambda functions are. That's where the Lambda functions are stored. I'm going to upload it to a S3 bucket. And then I'm going to give you a new SAM template, which is you're ready to be used. And the second command is really, so SAM package, and the second command is really SAM deploy. So those are the 2 commands that are available to you, which takes an existing zip bundle from your local machine, uploads it to the S3 bucket that you have specified, and then you are ready to roll with this. Okay? So as I said earlier, the SAM CLI is very powerful, because one of the biggest benefits that it gives you is, well, package and deploy are the commands, but it allows you to do local testing of your Lambda functions. And that is pretty stoke. So you can really easily test your serverless applications. It works with the Lambda functions. Well, how does it work locally? Well, for that, one of the partners have actually created a Docker image which mimics the Lambda runtime on your local machine. Okay, so the big advantage is particularly how you can easily test your Lambda functions locally on your machine is I am seeing all the logs on my local laptop. I don't have to look into the CloudWatch and drill down further and things like that. That really improves my agility and the speed of innovation on how quickly I can churn out the application, debug the application, and stuff like that. There are multiple languages supported, and C# is coming soon. And this is fully open source, okay? So now let's switch gears and talk about how can we look at our microservices and create them and deploy them using AWS Lambda. Well, of course, we create 3 different Lambda functions, web app, greeting, and name. Each microservice is also front-ended by an API gateway. So in case of web app, of course, I have /web app. In case of greeting, I have /greeting. And then I have /names/1. Okay, so I've just created those. And then once I do that, then essentially my web app is talking to those microservices. And behind the scenes, my Lambda functions could scale up and down. So that's a very typical architecture that we have seen and on how customers are deploying microservices using SAM. So you have your Lambda functions front-ended by an API gateway, and that's it. Okay. So let's take a look at it. What does it take to create my Lambda functions with SAM? And I'm going to skip to the next slide also, which also talks about how do you test and debug Lambda functions on your local laptop. So here is my template. In my template here, I'm saying this is a serverless function. This is my handler. This is my Java 8 runtime. And it is really pointing to the greeting.zip that is into my microservices greeting directory. Here's my memory size here. Here's my tracing enable. Here are the events that are triggering this particular API or this particular Lambda function. And it's just referring to greeting API. And in the greeting API is where I'm giving it the Swagger definition, that this is my Swagger definition. So it's very natively integrated right there itself. Based upon that Swagger definition is how your API gateway is created. I'm talking about a stage here, and we'll talk about that a little bit later, but ignore that for a second. Then I have something very similar to my names function, names API. Now I have my Swagger definition for names. And similarly, I have my web app function. And this depends upon these 2 APIs as well. So all of that is really defined in my SAM function or my SAM template very easily. Okay. So first thing I'm going to do is I'm going to use the functionality where I'm not anywhere connected mode. I'm not going to disconnect, but I'm going to just run it locally here. Okay. So I'm going to copy this command here. I'm going to start up here. Okay, so all I'm going to do is I'm going to fire up SAM local start API. It's going to start up my API server as well, and it's going to use the greeting sam.yaml, which is basically a file extracted only for greeting, and it's going to start up my API here. Okay, now once this is running, the Docker image name is lamci lambda basically, and in here now I can say curl http localhost. I think the port is, yeah, this one here. So I can just check how my greeting looks like. So you can see this is churning, and it returns howdy. And over here, I can see my logs if there are any. Okay, so that's pretty cool. So what I'm going to do is next, I'm going to start up my name service. And I'm specifying the port as well in the command. So I'm going to start on port 3002 here. And then I'm going to go ahead and borrow the command here. Okay, I'm going to test this command quickly. That okay? Oh, no, I don't want to run it again. I just want to test it. So I'm just testing, just show me the list of all the names. So here is showing me the list of all the names, and then I can start, using, say, okay, show me 0th name, and it says Penny, okay? And then here in my terminal itself, I can start looking at the different logs on how this will look like. And then finally, I can fire up my web app endpoint. Before I fire up my web app endpoint, look at the command here. I'm specifying a whole bunch of environment variables as well. And for that, if I go here, if I go to test, I have environment variables. And these are my environment variables, because these are pre-baked for me, that my host is Docker for Mac, because that's sort of the image where it's running. That's the host name for the Docker for Mac by default. And the host and the port and the path. So all those are defined. So let me go ahead and fire my here. And I can go ahead and copy the command here. And I can test my endpoint. So let's test the endpoint here. Oh, what? Oh, unknown host exception. What is this? Hold on. Which directory? Oh, wrong directory. Aha. Because in the microservices web app directory, it is configured to run only in the cloud. And this is the one that is done for configuring running in the local environment. So now if I go back here, now I can say, show me here. And you will see now it's spinning here, and it's spinning here. So that means it's getting the results from there. So you can start seeing the logs over here. And then finally you see the results, howdy Sheldon. So it's very easy to kind of start debugging or start at least building it locally here, okay? Now that's one part of it. I want to attach a debugger now, okay? So what I'm going to do is I'm going to cut down here. I just terminated my service over here, and I'm going to attach a debug port here, okay? So I'm going to just attach a debugger port here. Okay, so that's good to go. I'm going to access the same command here. And here I am in my debugger. So let's kill everything else that we don't need here. And I have a breakpoint set up over here. Okay. So this is good to go. So what I'm going to do is I'm going to fire up this command, and it's going to wait for me because the debugger port is attached. And now I can say run and debug, and I have a pre-configured configuration for me. Boom, it just connects right there itself, and I'm into the debugger mode now. So now I'm actually debugging my Lambda functions locally on my machine using whatever your favorite IDE is. So this capability is very powerful. Then you can start debugging the functions. And the point being, once you are done debugging, then you say SAM package, upload the code to S3, and SAM deploy, and be done with it. So really powerful, actually. All right. Let's take a look at it. Some of my Lambda best practices. Okay. So what we have seen, customers building Lambda-based monoliths. And what that means is they will build one Lambda function that is doing your get, put, post, delete for a variety of sources, variety of resources. So not a recommended pattern. You don't want to build a Lambda-based monoliths. On the other extreme, where we have seen, where customers are building Lambda-based nano services, where they're going to have one for HTTP GET, one for HTTP PUT, one for HTTP POST. So what's sort of the balance? Are you swinging too far in the pendulum? Are you building monoliths or nano services? So let's take a look at some of the Lambda best practices, okay? Do the handlers share code? If they do, then you think about it. What is your sort of context? What is your scope? If you're using Java, for example, think about how you can create your Maven structure so that your jar files are sort of the sharing mechanism by which you can share the code between different Lambda functions so that you're not duplicating the content or the code. That's the most important part of it. Do the functions share event sources? So you think about that part of it. If they do, then if they don't, then you can really split them into your own repos very easily, or their own SAM files. You also want to make sure that the SAM API, the SAM CLI, actually gives you a validate command. So make sure you validate your SAM template locally and even as part of your CI/CD pipeline. So that's an important aspect. Also, when you are creating your Lambda function, make sure you are separating your Lambda handler from the core logic. So in this case, for example, if you look at it, all I have is a public class book post handler, which is implementing a request handler, of course. In the handle request, I have save book method call, which is done separately, okay? Because that's where my business logic is implemented. And the whole advantage of that is, first of all, it's more unit testable. I can do a unit testing of just calling that save function. I don't know, if maybe coming from a different library altogether. So it allows me to be more unit testable. And the other part of it is, see how I'm getting the DynamoDB mapper outside the Lambda function. Now, we all know the Lambda function, there is a boot up time. Particularly in the JVM side of it, it takes a while, a few seconds for it to get warmed up. But once it warms up, then it's pretty rock solid. And then the same class is used potentially for multiple concurrent executions. So in this case, I don't want to connect to the database or create a new connection to the database every time a Lambda function is being invoked. So the fact that I made it static, I'm making connection to the database once, and just relying upon the fact that the concurrent executions are just multiple instances of the class, and the static DynamoDB mapper is shared across them. So those are some of the aspects that you want to understand when you're building your Lambda functions. Also, make sure you minimize the dependencies. We talked about that a little bit earlier, but make sure you're using the AWS SDK is very modular. So make sure you only pick the components that you need. I'm really a minimalist person. So I don't like bloatware generally. So in that sense, always look at it. What is the minimum sort of a SDK component that you need to package it in there? Another part is also how you want to use environment variables. So if you look at this, for example, I have AWS region and S3 bucket are the two environment variables. Well, first of all, AWS region is, there's an EC2 metadata API that exposes a whole set of environment variables to you automatically. The Lambda functions queries that EC2 metadata API and exposes them as part of your standard Lambda function. So start relying upon those Lambda functions, those environment variables. And then in addition, you can start introducing your own environment variables, which allows you to be a little bit more stage agnostic. So if I'm running in dev or prod or staging, you can start making decisions based upon those environment variables. Always, we talked about it, always self-contain your dependencies in the function. Yes, we have a Lambda runtime. When you say Java 8, we have certain SDK version over there, but we don't want your application to break in case we make some changes in the backend. So make sure you are using a shaded jar, packaging it up all together, and saying, what, this is what I'm relying upon. So it's a very important part of it. A typical question is, we talked about this earlier, how much CPU, how much memory, how much network? No, all we give you is one big dial, and that dial basically gives you the memory. And based upon the memory, we allocate the number of CPU as well. So an interesting experiment was done on this. Look at the GitHub repo at the bottom here. It talks about how much memory should you allocate. So what we're doing here is we're calculating 1,000 prime numbers which are less than 1,000,000, okay? And that function was done using different memory capacity, using 128, 256, 512, and megabyte and 1 gig. And if you look at it, the cost for running the function is very similar, but just because there is more memory allocated to it, there is more CPU allocated to it as well. 128 took almost 12 seconds, and 1 gigabyte took like 1.5 seconds. So same cost, but look at the time difference. So don't think that I should allocate less memory and because I don't want to incur costs. Sometimes allocating more memory may be far more efficient to you. And anyway, you are on a second billing, per second billing. So think about it that point of view. By the way, getting started with Lambda is really easy. First, 1,000,000 calls per month are free for you. If your application goes bigger than that, then I think it's worth paying money in terms of using Lambda in that sense. Another aspect that you want to think about from Lambda best practices is how Lambda functions have a hard limit for 300 seconds. They'll be terminated right there itself. You also want to think about how a Lambda function, the deployment bundle cannot be more than 50 megabytes. You can also think about how the expanded Lambda function cannot be more than 250 megabytes. So the common question is, should we go serverless? Should we go containers? So these are some of the constraints that you want to think about, that serverless, in that sense, is truly an event-driven architecture. It's really the glue between your different applications. And these are the limits that you need to be aware of. But when you are ready, you can of course, move to the containers land of it, okay? So I want to talk a little bit about, I'll show you an example of deployment pipeline, but before that, I want to talk a little bit about how do you manage different versions of Lambda functions. So every time you upload a new Lambda function, a new version is created for you. And of course, there is a latest version that is always available for you, okay? So in this case, if you look on the left side, for example, I have a my Lambda function. I have uploaded 8 different versions. And then I can create different aliases. In this case, I have a prod, a beta, and a dev alias. The dev is the one that is always pointing to the latest one. Then I have a beta, which is pointing to a slightly older version, and a prod is a much more stable version. So this allows me to innovate rapidly, continue to push out new versions, and at any point of time, I can change my alias to point to a particular version, okay? That's on the Lambda side of it. But that's not what is exposed to your customer. What is exposed to your customer is an API. And that's where the API gateway comes in. So in API gateway, remember we talked about stage? API gateway has different stages. So I can have a prod and a beta and a dev stage. So now all I'm doing is, oh, by the way, the prod stage is talking to the prod alias on the Lambda function. The dev stage is talking to the dev alias, and the beta stage is talking to the beta alias. So now your customers can be exposed to different environments, and it's just which of the stage is pointing to which of the alias of the Lambda function. You can manage what is the functionality that is being exposed. So let's talk about Canary deployment, and that's sort of the mechanism that we use in Lambda functions to do Canary deployment. We really use Lambda aliases to do traffic shifting back and forth between them, okay? Actually, I think I'll show code about this right away. In the SAM template, essentially, there is just one single attribute which enables Canary deployment for you, okay? And there are, one attribute, but it can take 3 different kinds of values. The first one is called as Canary X%Y minutes. And what it does is send X% of traffic to the new function. Wait for 5 minutes and shift all traffic. Now, as part of that, X and Y have certain predefined values, but what it also tells you is that how do I decide, should I shift the traffic or not shift the traffic? I actually have CloudWatch alarms set up right next to it, which are basically Lambda functions. So I'm saying is, okay, I'm deploying a new version of Lambda, shift 10% of the traffic to this new Lambda function, And if the CloudWatch alarms, which are basically Lambda functions, doing a pre and post checking, if those alarms look good, then shift the rest of the traffic. But if those alarms are triggered that, oh, your error rate has increased, or whatever your business logic is, then fall back. So you can quickly kind of start monitoring. It's very sophisticated, but very powerful. You can do what we call them as a canary deployment speed, so to say. In this case, what I'm saying is linearly grow the traffic every 5 minutes by X%. And then again, X and Y have predefined values. And of course, there is all at once that, okay, you know what? I'm deploying a new function, just move all the traffic to the new function. So these are canary deployment speeds that you can take a look at it on how these values can be impacted, and I think this is very powerful. All right, let me show you some canary deployments using SAM here. So here's the deployment pipeline. Well, the deployment pipeline part is actually repetitive. All I have is a AWS code pipeline, and I'm using a similar concept. Take my SAM template. I have 3 separate deployment pipelines running. At any point of time, I can push the code to any of the repo, and that will trigger the change in my Lambda function. And that's sort of how you want to think and create about it. But here, these are sort of my different allowed canary values. I'm just taking it a default. Okay, this is really my SAM template, essentially here. Here is where I'm defining what my Lambda alias is. The default is the prod here. And if I go down, so these are only my parameters here, okay? Now if I go down here, here I'm saying a deployment preference, okay? In the deployment preference, I'm saying the type is refer to the canary deployment type. And there I do have a default value, so I'll trigger that. And here is where I'm defining my alarms. These are basically my Lambda functions, okay? And could be really the aliases as well. So really, you can just specify what the aliases are, and then let the Lambda functions or behind the scenes SAM template take care of everything for you. You just define this in the SAM template and let the thing roll. So I think it's really powerful, so you should definitely take a look at that. Logging and metrics are a universal right. Everybody should have it. Without that, the application doesn't make sense, in my opinion. AWS Lambda, we provide you 6 inbuilt metrics for Lambda, and similarly for API Gateway. So you can take a look at those metrics and see how you can make sense out of it. These are the metrics that you can start utilizing, for example, for your canary deployments. Now you can say, hey, if this metrics, so write a Lambda function which gather that metrics and say if this metrics is above a certain threshold or below a certain threshold, I don't want to go ahead with the deployment. So I think that's an important part. You can also call put metric data from your function code for custom metrics. So these are pre-built, but then there are extension points available to you. There is, of course, we talked about, there's a native integration for AWS Lambda and X-Ray that's available to you out of the box. We saw this tracing sample. That's a very standard sample. Now, one of the questions our customers also ask is, okay, I got a whole bunch of Lambda functions. How do I manage these Lambda functions together in terms of a microservice? Let's say I'm not using Wildfly Swarm. Let's say I created these Lambda functions that are truly event-driven. How can I create a flow between them where I can say, when this Lambda function is called, then call this, and then this, and then this? Sort of a workflow diagram over there. That's exactly where AWS step functions kind of kick in. So think in terms of event processing. What I have is event A on B triggers C. So you can set up those Lambda functions together. Okay? All you want is a set of Lambda functions to invoke in a particular sequence. Now, we talked about how AWS Lambda is very event-driven, or like in the broader serverless platform. You have a whole variety of events, like about 18 events that could trigger a Lambda function essentially over here. So what you want to do is create a visual workflow on how this thing looks like, and then when it is executing, be able to see that this is actually working for me, okay? So this is one of the classic examples used by our customers, and some of the customers are listed down at the bottom, is as a user, I'm walking around, I take a picture on my cell phone, I upload it. Behind the scenes, the upload goes into an S3 bucket. There is a Lambda function that is running. It quickly, hey, new document uploaded to the S3 bucket. It takes a look at the document. It resizes it, to multiple screen factors and puts it into a different bucket. And then that is the bucket that is being used to serve the customers. Okay, so that's a very typical example. Seattle Times, and other customers that are listed here use that pattern. That's a very standard pattern that we have seen over there. And then this is where we're talking about the AWS step functions, essentially, on how you can visually compose the applications sort of in a workflow manner. There are parallel executions, there are serial executions, there are if-then-else loops, all sorts of stuff that you can show over here, okay? The last thing that I want to talk about, almost coming to the end of it, far end of it. So serverless application repository. So we talked about the Helm chart repository, in the Kubernetes world. So similarly, we have a serverless application repository, okay? Let's take a look at the code right away, actually. So serverless application repository really allows you to take code samples, deploy them, offer your solutions as a simple application. And it's really built on top of SAM concept. So you can take a SAM template and say, here is my serverless application, and I'm going to deploy this to my serverless application repository, which is, by the way, is publicly available for everybody. So you can look at the serverless application repository. You can publish your applications. You can look at the applications that are available over there and download them and run them in your own environment. So if you look here, let's go here first of all. So if I go to my serverless application repository, it shows what are the applications that are available over there. I can start searching. So if I search for microservices, somebody has published an AWS microservices application. That happens to be us. So anybody can go and click on the link and search for that application. So the SAM template that I talked about earlier is already published on the serverless application repository. The steps to publish are also given over here. An application packages SAM. You need to, of course, allow an S3 bucket, give it the right permissions, and then you publish the application. Okay. So the point being, you can look at the serverless application repository. You can click on the link over here which says deploy, and with that you have deployed that SAM template in your AWS account, and then you can start looking at it. It kind of gives you the README as well over here. That okay, once you have deployed it, then you just access the application, and that's it. And then you play around with it. So the SAM templates are available to you. It gives you the link to the repo as well, so you can start playing around with it. Okay. All right, that's pretty much the end of the presentation. I think we have pretty much consumed the entire 3 hours. So if you're looking at anything on Amazon ECS or AWS Fargate, those are your standard URLs, similarly for serverless and Kubernetes. And the workspace repo that we talked about earlier is available over here. So you can go to AWS samples, AWS microservices deploy options. And we have truly built this in a very open source way. So file issues, if things are not working, sharing is good. Sharing is good karma. So share it with your friends in your work. This is what we are recommending to our customers on how you should deploy microservices on the AWS cloud, whether it's using Fargate or EKS or Kubernetes or Lambda or any different ways. And most importantly, we are looking for your feedback. We're always looking for feedback from customers because that's what drives our roadmap in terms of what features, what services we should be looking at. Any questions for the last minute?
Oh, and one comment. If you want to look at all the different things for containers, you could just do aws.amazon.com/containers, and it'll show ECS, EKS, ECR, etc.
Yeah, both Tiffany and I are going to be here rest of the day. If you guys are interested, feel free to come by and talk to us. We'll be happy to answer your questions. All right, thank you so much.